Hi, I'm John Grafana, Senior Technical Staff Member and DevOps Champion at IBM Research, and I'd like to welcome you to Introduction to DevOps. This course will help you understand the cultural as well as technological transformation that is required to not only make your DevOps initiative successful, but allow it to flourish. According to a recent DevOps Institute report, demand for DevOps skills are expected to grow 122% over the next 5 years, making it one of the fastest growing skills in the workforce. Unfortunately, having skills alone won't ensure success. Gartner predicts that through 2022, 75% of DevOps initiatives will fail to meet expectations due to issues around organizational learning and change. I can't stress enough, the number one reason for failing to meet expectations is not around skills, it's not around tools, but due to issues around organizational learning and cultural change. Cultural change can have a significant positive effect on DevOps success. According to George Spafford, Senior Director Analyst at Gartner, people-related factors tend to be the greatest challenge, not technology. You see, DevOps is not a tool. DevOps is not a job title. DevOps is the practice of development and operations engineers working together through the entire software development lifecycle, following lean and agile principles that allow them to deliver software in a rapid and continuous manner. If you want to do it fast, you want to do it continuously, you need to adopt the shared mindset that is at the heart of the DevOps culture. So, how do you change a culture? In order to change your culture, you need to learn new ways of how to think, how to work, how to organize, and how to measure. Throughout this course, we'll look at how businesses are being affected by disruption and how a DevOps culture can help. We'll cover thinking differently through social coding and improving software reuse and sharing. We'll learn about ideas from lean manufacturing, such as working in small batches to reduce waste, creating minimum viable products to gain valuable insight. We'll explore working differently by using test-driven and behavior-driven development techniques to ensure repeatable behavior and high code quality. You'll see how adopting continuous integration and continuous delivery practices ensure that every change contributes to a potentially shippable feature. But tools are not the solution to a cultural problem. According to the 2021 Accelerate State of DevOps report by the DevOps Research and Assessment DORA team, which, by the way, represents 7 years of research and data from more than 32,000 professionals worldwide. Team culture makes a large difference to a team's ability to deliver software and meet or exceed their organizational goals. In order to change your culture, you'll need to organize your teams differently, because how you organize directly impacts the architecture and design of the products that you produce. You know, humans have a knack for figuring out what behavior is rewarded and then doing, or at least pretending to do, that rewarded behavior. For the last cultural change we'll discuss is measuring differently, and how changing your measurement system to encourage the correct behavior is critical for your success, because you get what you measure. We'll also look at how to avoid being fooled by vanity metrics and how you can use actionable metrics to gain valuable insight about your product and your customers. Implementing a DevOps initiative isn't easy, but it can be very, very rewarding. In order to really embrace the DevOps culture, you have to be willing to make changes. Lots of changes. You must be willing to experiment and understand that it's okay if an experiment fails, because every failure is a learning opportunity. So fail fast. You need to foster the core values of teamwork, accountability, and trust. So join me in exploring how you can transform the culture and technology of your organization so that your DevOps journey will be a successful one. Watch the videos, take the quizzes, and interact with your peers on the forums, because DevOps is a team sport and collaboration is encouraged. I like to say, we don't do DevOps, we become DevOps. After watching this video, you'll be able to describe how disruption facing companies today amplifies the need for DevOps. Since the year 2000, 52% of the Fortune 500 companies are gone. 52%. That's over half of the Fortune 500 companies that existed in the year 2000 are now gone. What were they up against? In a word, disruption. It's not if you get disrupted, it's when you get disrupted. Established institutions like banks might think, who's going to disrupt me? You can talk to banks about the need to deploy fast and use continuous delivery, but they're not always responsive. Then the bank down the street comes out with an app that can take a picture of a check and deposit it. Meanwhile, if it takes your bank 6 months to get your app updated to take a picture of the check to deposit it, your bank's going to lose a lot of customers in those 6 months. It's not a matter of if you get disrupted, it's a matter of when. If you talk to customers about being disrupted, a lot of them will say, oh, the technology disrupted me. I've been disrupted by technology. But if you think about it, the technology that was available to the disruptors is the same technology that's available to the incumbents, because most of it is open source. The disruptors just had a different business model. The example lots of people like to give is Uber. Uber's the big disruptor. So let's think about what was the amazing technology that allowed Uber to disrupt the taxi industry. Well, they had GPS, but GPS has been around for a while. We've had Garmin's and TomToms on our dashboard for years, so that's nothing new. That's fairly old technology. Then there's electronic payments. Electronic payments are older than GPS. They've been around for decades. And then there's a smartphone in every pocket. This is pretty commonplace as well, but Uber put the three of those things together with a new business model. Instead of waiting for a taxi to drive by or hailing a cab or making a phone call to a dispatcher, what if we allowed people to summon a driver from their smartphone? Let the driver know where they are, and then the nearest driver comes and gets them. And they can track where they are and when they'll be picked up. Uber had a different business model, and people loved it. It wasn't so much the technology, it was the new business model that allowed them to disrupt. In fact, here in New York State where I live, the taxi industry is lobbying Albany, the state capital, for legislation to limit Uber. The taxi industry doesn't need government legislation. They need to hire some programmers and get an app. Genie's out of the bottle. This is the way people want to do ride sharing. You either adapt or you go extinct. Disruption is everywhere, in every industry. When was the last time you used a travel agent? You do that on the web now. What about those little point-and-shoot cameras? That was a major industry, and everyone was buying them. Now, not so much, because everyone has a pretty good camera in their pocket on their smartphone. People used to say to me, what's the best camera to use for candid shots? And I'd say, the camera that you have with you, the one in your pocket. That's the one the best camera to use, right? So people don't generally need to have these point-and-shoot cameras anymore. They got disrupted by the smartphone. Think about Blockbuster Video. Back in the 80s, we would rent videotapes. VCRs were a big thing. And we'd physically go to the Blockbuster store, and if we brought the tape back late, they would penalize us. It was like checking a library book late, and we accepted it. Then Netflix came around, and Netflix realized DVDs had just come out. And the DVDs were a lot smaller than those big, bulky tapes, and they could mail them out. So the first business model for Netflix was that they would mail you a DVD, and then you'd have a list of DVDs that you wanted. And you wouldn't get the next DVD until you mailed the one you had back. If you kept it for 6 months, that didn't change. They didn't give you a late fee. They didn't care if you kept it for 6 months. You just didn't get another one for 6 months. You had to send one back before you can get another one. Then, after a while, Netflix realized that they didn't need DVDs. Everyone had broadband internet in their homes. So Netflix began streaming movies into the customers' homes. See, the problem for Blockbuster is that they thought they were in the video rental business. But Netflix understood they were in the entertainment business. They were in a totally different business. They were entertaining people now. And now they have their own shows on Netflix, right? Produced shows by Netflix. And Blockbuster went out of business. If you look at Garmin, they didn't do so badly. Garmin was able to pivot. When everybody had a GPS on their phone, they didn't need a Garmin on their dashboard anymore. But Garmin understood they were not in the mapping business. They realized they were in the tracking business. They started making little wrist trackers, right? Garmin made these trackers you could use to exercise and stuff. They pivoted, and they're still around. Some businesses survive, and some businesses do not. But the message here is that technology is the enabler of innovation. It is not the driver of innovation. You must have a great business model idea and a great model, and then leverage the technology. Technology alone is not going to drive innovation. It just enables it. In this video, you learned that technology is the enabler of innovation and the importance of having an innovative business model. After watching this video, you'll be able to describe how major companies are embracing DevOps and recognize that DevOps requires a cultural change. DevOps takes a completely different mindset, so you must first unlearn what you have learned. To really embrace the culture of DevOps, you must unlearn your current culture. It's easier said than done. For companies that are startups who are, not steeped in enterprise culture, it's easier. Right? New startups begin with a new culture. But the big enterprise businesses must unlearn what they have learned and change their ways. This is extremely difficult to do. But consider this. What if you could fail fast and roll back quickly? You could limit your blast radius of a change. You could put something out in production, and if it goes wrong, it doesn't bring the whole system down by limiting the blast radius of that change. What if you could test in market instead of second guessing and analyzing? Companies do this all the time. They'll be A/B testing. And you'll say to your friend, hey, did you see that widget on the website? You clicked on it, and your friend is looking at like, what are you talking about? Your friend didn't see it. They didn't see any widget. Your friend doesn't see it because the site was A/B testing. You were in the A group, they were in the B group. They didn't get to see that new widget. Companies take a subset of their customers and show them something new and see how they react, instead of trying it out on everyone. This is testing in market, and it can be very, very powerful. What if you had an application design that allowed you to change individual components to be replaced? You wouldn't have big bang releases. This is how apps like Spotify are designed. Spotify is not just one big monolithic app. It's a bunch of little microservices. So they have a recommendation engine, and it's a microservice, and it shows up in the app. And if they want to roll out a new recommendation algorithm, that team can roll the new recommendation out without affecting any other part of the app. You might make totally wacky recommendations, but it's not bringing the whole Spotify service down. You just get some recommendations that seem a little ridiculous, but you're listening to your music. What do you care? These are things that enable you to move fast in market. In 2009, at the Velocity Conference, opened a lot of people's eyes. John Allspot and Paul Hammond gave their now famous presentation at the Velocity 2009 conference entitled 10 plus deploys per day, DevOps cooperating at Flickr. Allspot was at Flickr at the time, and he talked about how they were doing 10 deploys per day, and people's heads exploded. 10 deploys per day, right? They were happy if they could just get a deploy out every 6 months. But they weren't deploying all of Flickr 10 times a day. People didn't realize this at first. They had a different application design. They were deploying little pieces. And this opened a lot of people's eyes to the possibility of what could be if Dev and Ops worked together to move things out, instead of Ops being the gate for Dev. In that talk, they said that in the last week, there were 67 deploys of 496 changes by 18 people at Flickr. And that was back in December 2008. In January 2011, Etsy talked about deploying to production 517 times that month. What they actually said is that in January 2011, a month that they had over 1 billion views, their code was committed by 76 unique individuals and deployed to production a total of 517 times. I did a little back of the napkin calculation, estimated they're deploying like every 25 minutes. Right? People looking at this and saying, how are they doing it? Chad Dickerson was the chief technology officer at Etsy at the time. He said that Etsy's deployment environment requires a lot of trust, transparency, communication, and discipline across the teams. He and his teams work together for a common goal, not working against each other in silos. You might think, These are mythical companies, right? These are the sparkly unicorns. You could never do this in a big enterprise. No way, no how. Enterprises cannot change and move that fast. They just cannot do it. Won't happen. Then in 2016 at the DevOps Enterprise Summit, which 1,300 attendees, Gene Kim from IT Revolution, author of the Phoenix Project, began outlining where the industry stands and what's driving DevOps adoption in the enterprise. You had major companies like Ticketmaster, Nordstrom, Target, USA Today, ING, major retail companies, insurance companies, banks, standing up and singing the praises of DevOps. This is when other enterprises started to notice this DevOps thing. It's not just for startups. It actually works in big enterprises. Ticketmaster talked about 98% reduction in mean time to recovery. Traditional IT is measured in mean time to failure, but DevOps is all about mean time to recovery. Stuff is going to fail. How quickly can you recover is the question. Nordstrom had achieved 20% shorter lead times. Target's full stack deploy went from 3 months to minutes. Obviously, they did a lot of automation. Sometimes that 3 months is not all work, though. Sometimes the 3 months is having to go before a change review board. And they only meet the first Tuesday of every month, and today is Wednesday after that Tuesday. So I have to wait another whole month to get something reviewed. This is how big corporations work. If you want to move faster, you have to break down those barriers and to push changes faster. USAA releases went from 28 days to 7. That's pretty good, from a month down to a week. And ING has 500 application teams doing DevOps, and CSG went from 200 incidents per release down to 18. That's amazing. These are major companies that are singing the praise of DevOps at the DevOps Enterprise Summit back in 2016. People were starting to take notice. This is not just the unicorns anymore. So, how are they doing this? What's their secret? Is it some magic tool, and where can I buy it? No. They have embraced the DevOps culture. It's not a tool that they bought. It's not some procedure that they follow. They actually change the culture of their company. Something very, very hard to do, but necessary to gain the advantages that DevOps has to offer. Until and unless you change the culture of your company, you will fail at attempting DevOps. Because DevOps is not about tools. It's about trust, transparency, communication, coordination, and discipline. You can't buy DevOps in a box. In this video, you learned the impact of John Allspaugh's 10+ deploys per day DevOps at Flickr in 2009, and that DevOps is a cultural change that requires trust, transparency, and discipline across teams. After watching this video, you'll be able to define DevOps and describe the essential characteristics of DevOps. What is this DevOps all about? One thing is for sure, it's an overused buzzword in the industry. If you ask 10 people to define DevOps, you get 11 different answers. Because of this ambiguity, let's go back to its inception and work our way forward. In 2009, Patrick Dubois coined the term development operations. He said, development operations is an extension of agile development environments that aim to enhance the process of software delivery as a whole. It's an extension of Agile. We're going to talk about what Agile did for the devs and how it did nothing for ops. Patrick Dubois is saying, what if we applied Agile to ops? What if we treat them the same? This is why sometimes I call DevOps Agile for ops. This makes the ops as agile as the devs by working together for a common goal. Patrick Dubois was just saying that dev and ops can and should work together. DevOps is a recognition that development and operations must stop working in silos. They have to start working together. I like to say DevOps is the practice of development operations engineers working together during the entire development lifecycle, following lean and agile principles that allow them to deliver software in a rapid and continuous manner. I want to do it fast. I want to do it continuous. And I want to do it with dev and ops both together through the entire software lifecycle. To do that, we need to change to a culture of collaboration that values openness, trust, and transparency. We must adopt a new application design that does not require entire systems to be redeployed just to add a single function. You're not going to be able to deploy these large monolith applications 10 times a day. We need automation that accelerates and improves the consistency of application delivery so that we can deploy and deliver our software with speed and stability. Once we take that application, we split it up into lots of little microservices. No human can deploy it anymore. So we need automation to automate the deployment of all those tiny microservices. We solve some problems with applications. We create some new problems with microservices. We solve those problems with automation. Happens all the time. Finally, you need a dynamic, software-defined, programmable platform to continuously deploy onto. You can't be waiting days or weeks for somebody to provision a server and configure that server so that you could deploy your application. You have to say, I need an environment and I need it now. And you get that environment to come up, deploy your app, and your software is up and running. Now, it's important to understand what DevOps is not. DevOps is not just development ops working together. It's a cultural change. DevOps is not simply combining the dev team and the ops team and you're done. No. DevOps is not a separate team. I've seen companies make DevOps teams. It's not a separate team. If you know anything about Agile, you don't make an Agile team. You don't say, oh, we have that team over there. They're the Agile team. They make us Agile. No. Instead, the whole company becomes Agile. DevOps is not a team. It's just like Agile. And DevOps is not a tool. There are many tools that support DevOps. These tools can reinforce your DevOps culture, but they will not change your culture. You cannot become DevOps by simply buying a set of tools. And there is no one-size-fits-all strategy. This is what makes it difficult. You must find out what works for your business. Are you shipping shrink wrap software? Do you provide software as a service? Is your product or software that people download and install themselves? It'll be different based on what you're delivering, and you might not be delivering software at all. You might be delivering a service that software just enhances. So it's really important. Finally, DevOps is not just about automation. This is the one where DevOps engineer jobs come from, right? People think that if they hire somebody who knows all the DevOps tools, then that person can automate everything and make them DevOps. This is not DevOps. The devs are still doing the same thing. It's not just ops automation. That's all it is automating ops. So DevOps is not just dev and it's not just ops. It's DevOps. One word, one team, one set of measurements. In this video, you learn that DevOps is not just dev and ops working together while remaining in their separate silos. DevOps is a cultural change in which development and operations engineers work together during the entire development lifecycle. After watching this video, you'll be able to describe how applications evolve to give rise to DevOps, list the 3 dimensions of DevOps, and describe some essential characteristics of DevOps. Let's not lose sight of the goal. What is the goal? Agility is the goal. You want to be doing smart experimentation. You want to be moving in market with maximum velocity and minimum risk. This way, you can gain quick, valuable insights to consistently change the value proposition and the quality that you deliver to your customers. There are 3 pillars for agility. One of the pillars is DevOps. This includes cultural change, automated pipelines, infrastructure as code, and immutable infrastructure. The second pillar is microservices and includes loosely coupled application design using microservices that communicate via REST APIs. Microservices are designed to resist failure and tested by breaking them and failing fast. The third pillar is containers. Containers are development-centric environments that give us portability and fast startup. They also enable an ecosystem that allows quick deploys with immutable infrastructure. I like to call this the perfect storm. Taken separately, these are impressive technologies on their own, but together they enable powerful change. You have DevOps for speed and agility, microservices for small deploys, and containers for ephemeral runtimes with fast startup. Ephemeral means lasting for a very short time. They're ephemeral because when a container goes bad, we don't try and fix it. We just delete it, replace it with a new one. These are throwaway runtimes. Tony Stafford says, DevOps starts with learning how to work differently. It embraces cross-functional teams with openness, transparency, and respect as pillars. That's a tall order. Does your organization embrace openness, transparency, and respect? That's what's required to become DevOps. Let's talk about application evolution for a moment. In the past, there was waterfall with its monolithic applications deployed on physical servers, and then at some point in time, we migrated to Agile and used service-oriented architectures and virtual machines. And then DevOps followed, and now we're using microservices deployed in immutable containers. This has been an incremental evolution. We broke the monoliths into services, and the services were still large with service-oriented architecture. But we had embraced services as a design concept. Then we had virtualization in the cloud. This made things much smaller. And with DevOps, we have evolved again into microservices and containers to deploy them in. DevOps has 3 dimensions: culture, method, and tools. Most companies focus on the tools. Most vendors focus on the tools as well because that's all they can sell. Some companies also focus on methods, which are important, but the most important thing to focus on is culture. Atlassian says, culture is the #1 success factor in DevOps. Building a culture of shared responsibility, transparency, and faster feedback is the foundation of every high-performing DevOps team. If you want to be a high-performing DevOps organization, you need to change your culture. While tools and methods are important, it's culture that has the biggest impact. So, how do you change your culture? Culture is ingrained within us. It defines who we are. It includes elements such as language, our food, our values, our stories. It's extremely hard to change a culture. Countries have cultures. Companies have cultures. Many companies attempt to become DevOps, but fail to change their culture. This change must come down from the top and embrace from the bottom up in order for this change to happen. This is not an easy thing to do. So, how do you change a culture? You must change the way people think. They have to start thinking differently. You need to think about social coding and sharing. You have to change the way they work. You need to start working differently, working in small batches, using test-driven and behavior-driven development. You must change the way you're organized. A lot of companies don't get this. You must organize differently because organization has a direct impact on how you build things. Most of all, you must change the way people are measured. You must change your measurement system and measure differently because you always get what you measure. In the remainder of this course, we're going to explore the DevOps way of thinking, working, organizing, and measuring. In this video, you learn that applications evolve from waterfall development of monoliths to agile development of microservices. DevOps has 3 dimensions: culture, method, and tools. And the essential characteristics of DevOps includes cultural change, automated pipelines, infrastructure as code, microservices, containers, and immutable infrastructures. After watching this video, you'll be able to describe the problems with the waterfall method and describe the typical relationship between software development and operations prior to DevOps. It's important to understand what brought us to DevOps in order to fully appreciate the problem that it solves. Architects would spend months and months designing the system on paper, creating requirements documents, creating design documents, making high-level designs, low-level designs, system-level designs. Then, finally, we get to the development phase, where development worked for months and months on features in an isolated development environment. As they developed the code, if the designs are wrong, it was very expensive to go back to the architects. Once we developed all the code, we'd get to the testing phase, and we'd test all the code at once. And testing would open defects, send the code back to development until no more severity 1 or 2 defects were found. At some point, Development would release the code to operations for deployment. This release to deployment would happen several months after the code was written, maybe even a year later. Some of these projects took up to 2 years. Then the operations team would take what seemed like forever to deploy it because they had no idea what the developers had built. An operations team kept running it from that point on. We call this way of working the waterfall method. With waterfall, everything happens in phases. Requirements are gathered and a requirements document is generated. Then that phase ends. The artifacts for that phase flow down to the next one. In the next phase, we do all the design, and the design is documented in high-level designs, low-level designs, system-level designs, and that phase ends. Those artifacts get passed down to the next phase, and the coding begins, where developers take those low-level designs, the design documents, and write the code that implements those designs. There are entrance and exit criteria to each of the phases. So all along, we're coding in isolation. We're not integrating my module with the next person's module. Finally, you get to the integration phase when all those modules come together. This is the first time we realize we don't know whether all these pieces even work together. And then we move on to the testing phase, because now we've got a system that people can test. And as they find bugs, they must go swim back up the waterfall and open some bugs in the coding phase and do some recoding. Finally, after all that testing, we deploy the software. It's called waterfall because if there's a problem, it's very hard to go back, like trying to swim up a waterfall. You have to go all the way back to the design phase. In fact, because we treat software development like civil engineering projects, sometimes those designs have moved on, right? The architects moved on, the designers moved on to the next project, and you've got to go find them and get them to change the design. Then you get the developers to change the code in hopes that it integrates this time. This process was very error-prone, and there was no room for making changes late in the process. You didn't know whether it worked until the end, so it was very high risk. But we developed software like this for years. So what's wrong with this approach? Well, there's no provision for change. Every phase has entrance and exit criteria. When one phase ends, the next one begins. And there's just no provision for going back and changing the design or changing the requirements or anything like that. Another problem is you don't know if it works until the end. There is no intermediate delivery. Nothing is delivered until that last step when we give it to the operations team and say, go deliver the thing to production. In addition, with each phase, there are issues that are just passed down. And of course, every one of these is an opportunity to lose information and to have a mishap. People get blocked because they can't accept the work from the previous phase, and then the next phase is delayed. Mistakes that are found later are very, very costly. It's especially costly to find something that's in design wrong in the testing phase and then go all the way back and redesign it. Finally, these delays create long lead times between deliveries. Also, the overall problem with waterfall is that the teams are working separately. They're unaware of their impact on each other. Designers are unaware of the impact of the code. The coders are unaware of the impact on testing or impact on integration before we get all the code together. So everybody's working in their silos for their phase. And the scariest thought is that the people who are furthest away from the code, the poor operations team, have to deploy it and run it and manage it in production. They know the least about the code, and they're the ones expected to run it. In this video, you learn that traditional waterfall development creates problems such as delays, frustration, long lead times, expensive late changes, and operations managing unfamiliar code. And that in the past, software developers and operations worked in silos rather than working together. After watching this video, you'll be able to describe how extreme programming was the beginning of Agile and describe Agile and how it became part of DevOps. In 1996, Kent Beck came along with extreme programming. Kent based this on an iterative approach. He described these feedback loops. Release plans take months, iteration plans take weeks, acceptance plan takes days, stand-up meetings are conducted every day, and pair negotiations are done every hour, and unit testing in minutes and programming in seconds. These tighter and tighter loops represent the approach. The idea was to improve software quality and get feedback quickly, get something out to the customer, get feedback quickly, and then iterate on it. Extreme programming was intended to improve software quality and responsiveness to changing customer requirements. It emphasized concepts like pair programming. I encourage you to try pair programming. It gets two sets of eyes on every line of code and helps cross-train your team with skills. For example, a person who really knows Python will pair with one who's just learning Python. And they work together, and the junior programmer gets to see how the senior programmer approaches the problem. Pair programming is a great way of mixing the skills in your team and getting everyone under the same code to understand it at the same time. Kent Beck's extreme programming was one of the first Agile methods. In 2001, 17 software developers met in a resort in Snowbird, Utah to discuss these lightweight development methods. What they came up with is called the Agile Manifesto. The Agile Manifesto emphasized valuing individuals and interactions over process and tools, working software over comprehensive documentation, customer collaboration over contract negotiation, and responding to change over following a plan. That is to say, while this valued the items on the right, we value the items on the left more. It was a big breakthrough. People began to change their organizations to be agile. In agile development, requirements and solutions evolve through a collaborative effort of self-organizing cross-functional teams and their customers. It advocates adaptive planning, evolutionary development, and early delivery, and continual improvement. It also encourages rapid and flexible response to change. Work is done in increments called sprints. Planning is adaptive. We plan for the next 2 weeks, and then the 2 weeks after that, and then the 2 weeks after that. Agile includes continuous improvement, that is asking what you learned and what you're going to do to change. The devs were latching onto it, and I was in a couple of Agile teams back then, and it was really working out well. But being Agile doesn't solve all the problems. There are still ops to consider, and Agile was in direct opposition to the way operations was being measured. I was on a project that illustrates this concept. We started the project in January. Toward the end of February, we had code we actually wanted to deploy. We went to the ops team to deploy it, and they said, open a ticket. So we opened a ticket to get 3 VMs. And a couple days later, we asked about the VMs. It takes 20 minutes to make a VM. And the ops team said, it takes 2 weeks to find a person who has the 20 minutes to make the VM. The ticket sat, and then it was kicked back. The project was deployed in September, and I left the project in December. I couldn't take it. It was crazy that the developers were being agile, working in sprints, and then waiting for the ops team to deploy something. Agile alone is not good enough. Patrick Dubois had the realization that we need to make ops people agile. The result of this situation is called two-speed IT. Here's how it works, or rather doesn't work. A developer needs some resources. Ops tells him, submit a ticket. The developer says, never mind, I'll go to the cloud. And the developer goes to the cloud and gets the resource immediately instead of waiting for days for his IT organization or service a ticket. This is the slow speed of going through the company resources and the fast speed of getting resources outside the company. This is how shadow IT gets started. There are resources that the business doesn't know about because people go around the IT shop because IT is not meeting their needs. Then the cloud makes this very easy to do, and I would bet that every organization has users with cloud accounts and no one IT knows about. We need a solution to this problem, and DevOps is an answer. In this video, you learn that extreme programming paved the way for Agile development, and Agile emphasizes valuing individuals, collaboration, responding to change, adaptive planning, early delivery, and continuous improvement. After watching this video, You'll be able to list key examples of DevOps growth that occurred from 2007 to 2019 and summarize the contributions of key influential people in the growth of DevOps. I'd like to take you through a brief history of some significant events in the early DevOps movement and point out who the key influencers were. DevOps really started in 2007 when Patrick Dubois recognized that Dev and Ops weren't working well together. He wondered if there was a better way. The next year, at the 2008 Agile conference, Andrew Clay Schaefer created a Birds of a Feather meeting to talk about Agile infrastructure. Schaefer didn't think anybody would come, so he did not show up to his own meeting. Patrick Dubois showed up, and Patrick went to looking for Andrew because he wanted to talk about Agile infrastructure being a solution to get operations to be as agile like the developers were. This is where DevOps got started. Then in 2009, at the Velocity Conference, John Allspaw gave a talk about 10+ deploys per day, Dev and Ops cooperation at Flickr, and the idea started gaining traction. This talk made people take notice of what was possible by adopting these early DevOps practices. Also in October 2009, Patrick Dubois, often called the father of DevOps, held the first DevOps Days conference in Ghent, Belgium. It was described as the conference that brings development and operations together. This is where the term DevOps was first used. DevOps Days is now a local conference held internationally several times a year in different cities. In 2010, Jez Humble and Dave Farley wrote the groundbreaking book called Continuous Delivery that sets out the principles and technical practices that enable rapid, incremental delivery of high-quality, valuable new functionality to users using a technique called continuous delivery. Through automation of the build, deploy, and test process, along with improved collaboration between developers, testers, operations, delivery teams can release changes in a matter of hours, sometimes even minutes, no matter the size of the project or the complexity. This book is over 10 years old, but it still has a lot of great concepts that help change a lot of people's thinking about how to perform software delivery in a continuous fashion. In 2013, Gene Kim, along with Kevin Bear and George Spafford, published The Phoenix Project, a book based on Elijah Goldratt's book, The Goal. The Goal is about a manufacturing plant that is about to go under and what they had to do to bring it back to life. It's a story about lean manufacturing principles. The Phoenix Project is about an information technology shop in a company that's about to go under and what it took to bring it back to life. This story is about applying lean manufacturing principles to software development and delivery. In 2015, Dr. Nicole Forsgren, Gene Kim, and Jez Humble founded a startup called DORA, DevOps Research and Assessment, that produced what are now the largest DevOps studies to date, called the State of DevOps Report. Nicole was the CEO and is an incredible statistician, and through this research, she found that taking an experimental approach to product development can improve your IT and organizational performance, and that high-performing organizations are decisively outperforming their lower-performing peers in terms of throughput. The research shows that undertaking a technology transformation initiative can produce sizable cost savings in any organization. If you haven't read this year's State of DevOps report, I strongly urge you to do so. The DevOps Handbook was published in 2016. It was written by Gene Kim, Jez Humble, Patrick Dubois, and John Willis as a follow-on to the Phoenix Project, and it serves as a practical guide on how to implement the concepts that were introduced in that book. John Willis, by the way, worked at Docker and Chef back then and is a DevOps Days coordinator after being at the original DevOps Days in Ghent 2009 with Patrick Dubois. If you only read one DevOps book, this is the book to read. They look at companies that have adopted DevOps and document what did work and what did not work. It's a great read. Over the past 10 years, there have been 40 DevOps Days events in 21 countries, and it's growing. Patrick Dubois was the lead for DevOps Days from its inception in 2009 until 2015, and then Bridget Krumhout became the lead in 2015. She's also a co-host on a very popular podcast, Arrested DevOps. If you don't listen to it, you should. I've learned a lot from listening to Bridget. She's heavily involved with the DevOps community. She stepped down in 2020, but stayed on the advisory board of DevOps Days, and it is a great event. I got to attend DevOps Days in New York City in March of 2020, and I loved every minute of it. These are some of the major influential people in the early DevOps movement. Patrick Dubois, Andrew Clay Schaefer, John Allspaw, Jez Humble, Gene Kim, John Willis, Bridget Crumhout, and Nicole Forsgren. They weren't the only ones, but they went out and made a difference. They showed us how DevOps can be impactful. They explained that it's all about changing culture, not just about tools. They explored measurements and the idea of changing how you work. These are the early pioneers. Why is this history important? It's important because DevOps was a grassroots effort started by people like Patrick Dubois, who just wanted to eliminate the roadblocks in software delivery and figure out how can development and operations work better together. Damon Edwards, who co-hosted a podcast with John Willis called the DevOps Cafe, said it best in his talk on the short history of DevOps way back in 2012. DevOps is from the practitioners by practitioners. It's not a product, a specification, or a job title. It's an experience-based movement that is decentralized and open to all. People were beginning to realize that DevOps was a better way to work. In this video, you learn that Patrick Dubois started the DevOps movement in 2007 with a simple idea of getting development and operations to work better together. DevOps grew through the efforts of influential people such as Patrick Dubois, Andrew Schaefer, John Allspaw, Nicole Forsgren, Bridget Crumhout, Jez Humble, Gene Kim, and John Willis. After watching this video, you'll be able to describe social coding principles and recognize how pair programming creates better code and better programmers. What is social coding? I like to call it open source for inner source. Social coding is something that the open source community has been doing for years. What's new is bringing these concepts into the enterprise and coding as a community on internal projects. In the past, developers worked in private repositories, and you had to be a member of the team to contribute. Everything was controlled by access control lists and a strict need-to-know basis. The problem with that is no one knows you're working on it. So there's no possibility of reusing code because no one even knows it exists. So enterprises continually reinvent the wheel because no one knows the wheel has already been built. With social coding, repositories are public, and everyone's encouraged to fork the code and contribute. This is a hugely different way of thinking. Development teams love to think, this is my code, no one else can touch it, but they need to get over that for the good of the company. You would think that anarchy would ensue, but actually it works quite well because it's controlled by the repository owner. The person who owns the repository is still in complete control of the contributions. What problem is social coding solving? Well, let's say you see a component. It's 80% of what you need, but there's some missing features. How do you add those missing features? You now have a decision to make. Do you make a feature request to the repo owner for a new feature and risk that your request will be at the bottom of their priority list, or worse, their funding gets cut and your request will be cut out first? Or do you rebuild 100% of the code just to get the 20% that you need, so as not to have a dependency on another team? It's sad to report, but many teams select the latter and reinvent the entire wheel just to get the functionality they need. This is a huge waste of resources for any company, but it happens all the time. So, how does adopting social coding principles solve this? Well, you discuss a new feature with a repo owner, and you agree to develop it for them. This allows you to leverage everything that they've done and add the feature that you need. You open up a GitHub issue, and you assign it to yourself so everyone knows you're working on it. Then, you fork the repo, create a branch, make your changes. When you're all done, you have something to contribute back. Well, then you issue a pull request and signaling that you're ready for review. The repo owner can decide whether to merge your code back into the main project. The repo owners are in full control. They can ask for changes because they do the merge. They can ask you to write more test cases if you don't have adequate test coverage. They treat you and your contribution like any other member of the team. This is a win-win situation. You get to leverage another team's code and all the functionality that you need. And the other team gets a feature added for free. The company saves money because code's being reused instead of rewritten, and everyone is happy. This is how open source works, and this is how companies should treat their inner source. Pair programming is an aspect of social coding that is taken from extreme programming. It consists of two programmers sharing a single workstation, one screen, one keyboard and mouse between the pair. The programmer at the keyboard is usually called the driver. The other programmer, also actively involved in programming tasks but focused more on overall direction, is called the navigator. While the driver is typing, the navigator is checking their work, or perhaps looking something up, or thinking about what's coming next. Then after about 20 minutes, they swap roles. This way both get to play each role. I pair program whenever I can at work. I like this aspect of social coding. One of my personal weaknesses is that I'll agonize over what to call a new variable function. I want to get it perfect, to make the code as readable as possible. Having someone else to bounce ideas off of helps me make those decisions faster. You might think that pair programming is using twice the resources to get the same amount of work, but it's not like that. There are many benefits of pair programming. The first benefit is higher code quality. There's something about programming out loud that leads to clearer understanding of the code. In the past, when I wrote code, I wrote it alone, and then I explained it to someone, I would pick up on a bug as I was talking out loud. Like, I didn't see the bug when I was looking over the code in my head, but I saw it as I talked out loud. Having to explain code to someone forces clarity. This means that defects are found earlier, and that's a good thing because it lowers the maintenance cost right down the line. The later a defect is found in the process, the more it costs to fix. Pair programming also forces skills transfer, creating better programmers, like pair junior programmers, developers with senior developers. I do this all the time so that each one learns from the other's approach to a problem. They pick up tips and tricks that the other one uses, and it creates better programmers. You also get two sets of eyes on every line of code. You don't want code that only one person understands. Then that person goes on vacation. No one knows how to fix their code. Pair programming leads to better understanding of the code. More people understand the code well enough to fix and enhance it. In this video, you learn that social coding is done communally with public repositories, and all team members are encouraged to contribute. Pair programming results in higher quality code because defects are found earlier, costs are lowered, and there is a broader understanding of the code base. After watching this video, you'll be able to explain how the Git feature branch workflow supports social coding. Let's talk about guidelines for your repositories and workflow. Create a repository for every component, whether it's a microservice or something else you're building. Don't put multiple microservices in one repository. These are called monorepos and are frowned upon. People often create what we call a monorepo, which is a single repo with multiple microservices in it to make demonstrations easier. But this should not be done for production code. You don't want someone to have to check out a lot of code that they don't care about just to get to the code that they do care about. You want to have one component or microservice per repo. This is very important. Don't be afraid to have multiple repos. Create a new branch for every issue that you're working on. You don't want to have long-lived branches. I don't believe in having a development branch that all the work gets merged into and done. That's the old way of thinking. Branches are very lightweight in Git. There's a master branch and there are feature branches, and that's all there is. When you're done with the feature branch, you delete it. You don't get too attached to it because you delete it, you create a new one for the next issue you're working on. Use pull request to merge your code back to master. The only way code should get into the master branch is through a pull request. A pull request gives an opportunity for other people to look at your code and review it. Never merge your own pull request. Just don't do it. You always want to have someone else on the team merge your pull request because every pull request is an opportunity to have a code review. Have them look at the code, make sure it makes sense to them, and then have them do the merge. This way you get two sets of eyes on all the code that's going into the repository. We call this the Git feature branch workflow, and here's how it works. Let's begin with the GitHub repo. You create your new repository for your component Or if you're contributing to someone else's component, you fork an existing repository. Next, you clone that down to your workstation and it becomes your local repository. All of your changes will be made in this repository. Next, you create a branch to work on your feature. This can also be followed for bugs or other fixes. It's called a feature branch, but the idea is that it's the branch for the code that is associated with the GitHub issue that you're working on. When you're ready to submit your code back to the main project, or if you just want someone to review your code, your changes, and get feedback, you push your code to the remote branch. Finally, you create a pull request that your changes be reviewed. The pull request will be reviewed, and if the code is complete and meets the standards set out by the team, it'll be merged back into the master branch and become part of the original GitHub repository. In this video, you learned that creating a repository for every component, following the Git feature branch workflow, then creating branches and using pull requests is a good practice. After watching this video, you'll be able to explain working in small batches and recognize how single-piece flow yields faster feedback. Working in small batches is a concept from lean manufacturing. It's important in situations where fast feedback is required because it enables you to learn quickly from your decisions. You may be testing a hypothesis and you don't want to get too far before you know if it's going to work. Working in small batches allows you to experiment more in order to quickly gain insights. In contrast, working in large batches that take months to complete means you don't get feedback for months. Working in small batches also minimizes waste because you gain feedback faster and you don't waste time developing things your customer doesn't like. Using large batches, you may spend months developing something that isn't what the customer wanted. In keeping with DevOps practices and cross-functional teams and lightweight approaches, the best way to rapidly progress from development through test and operations into production in a matter of minutes is working in small batches. Let's take a look at an example of working in large batches versus small batches. Let's say I need to mail out 1,000 brochures. And the steps are, I fold the brochures, insert the brochures into envelopes, seal the envelopes, and then stamp the envelopes with postage. We'll use this brochure example to compare large batch and small batch execution. Let's say that I'm going to process the first 1,000 brochures in batches of 50. These are large batches with 50 brochures in each batch. Assume that each step takes about 6 seconds to complete, so I can do about 10 steps per minute. I start with the first step, which is folding, and at 10 per minute, it takes me about 5 minutes to fold 50 of them. Then I move on to the next step. The next step is inserting them all, and I can do about 10 of them per minute, so it takes me 5 more minutes. Plus the 5 minutes before, now I'm 10 minutes into it. Once I have them all folded and I inserted, I move on to the next step, which is sealing them all. If I'm sealing 10 per minute, I could do another 50 and another 5 minutes. So I'm up to 15 minutes at this point in wall clock time. Finally, I get to the step 4, stamping, and it took me 16 minutes to get my first finished product. This is the first time that I have things that I can actually inspect to check the quality. What if the envelopes had no glue? It would be 11 minutes before I figure out that something went wrong. What if there's a typo in the brochure? I have to go all the way back to the beginning. So this is very wasteful working in these large batches. Now let's look at the same example with small batches using single piece flow. Again, assume each step takes about 6 seconds to complete. With single piece flow, I fold one and I put it into an envelope and I seal it and I put a stamp on it, and the first finished product is about 24 seconds. Now I can inspect it and see if it works, see if it's what I thought it was. And then let the rest of the flow continue if it was acceptable. I receive fast feedback in only 24 seconds instead of 11 minutes with a large batch. Now, what if the envelopes had no glue? I'd find out in about 18 seconds. And if there was a typo in the brochure, after 24 seconds. It's very important that we don't work in large batches. We need fast feedback so that we can quickly pivot if we need to do something different. Working in small batches helps you implement other DevOps practices like continuous integration and continuous delivery. So how do you know if your batches are small enough? I would start with the size of your stories in your backlog. Are your application features decomposed in such a way as to support frequent releases? You have to ask yourself, how often are releases possible? Are there delays in release because the features are too large? Can features be completed in a sprint? If you have features that take several sprints, then your batches are too large. Ultimately, a feature should be small enough to be completed in a week or less. The features you build are one step towards a goal. Many people feel that only a completed goal is worth shipping, instead of thinking useful subsets that can be delivered in increments to gain feedback towards the ultimate goal. In this video, you learned that working in small batches means delivering something useful quickly, and using single-piece flow leads to faster feedback loops. After watching this video, you'll be able to define a minimum viable product and recognize how an MVP should be used to give the customer what they really want. Let's talk about a minimum viable product. First, let's understand what it is not, because there are some misconceptions that a minimum viable product is the same as phase 1 of a project or the first beta or something like that. This is not what a minimum viable product is. A minimum viable product is the minimal thing that you can do to test a value hypothesis and gain learning and understanding. You might say it's the cheapest thing you can do to prove a hypothesis. You can finish the first MVP, then you get the results and move on to the second one and so on. The difference between these two is that the first one is all about delivery. What am I going to deliver? But the second one is all about learning. What can I learn? What can I learn from putting out this MVP and getting feedback and then maybe making the next one even better? So it's important at the end of each MVP, you decide whether to pivot or persevere. Should I pivot? That is, do something different, or persevere, continue doing what I'm doing. Let's look at an example. Here's a team that's developing a minimum viable product for a customer that wants a red car. And so in the first iteration, they deliver a wheel. And the customer's like, what am I going to do with a wheel? I can't do anything with this. Well, we're working iterations, they say. We're trying to be agile here. In the next iteration, we'll give you something more. And they give the customer a chassis. And the customer responds, I still can't do anything with this chassis. And then they give them a car with no steering wheel. And eventually, they get the whole car. Now the customer gets this coupe. And there's no feedback along the way. The team didn't know until the end whether the customer is going to like what they built or not. The team did not understand how to create a minimum viable product. They were just doing iterative development with no regard to whether each increment was useful or not. The second team understands the value of creating an MVP. At first, they give the customer a skateboard, and the customer says, what's this? I asked you for a car, you give me a skateboard. And the team said, no, wait. We're testing the color. How do you like that color red? Is that the color you want? The customer says, oh yeah, red's kind of cool. It's really hard to steer though. So team says, no worries. In the next MVP, they give them a way to steer it. And the customer says, well, okay, you did give me a way to steer it, but I can't go very fast. I need a better form of locomotion. And so the team deals with that in the next MVP. In the next iteration, they give them pedals to go faster. Somewhere along the way, while riding on that motorcycle, feeling the wind in their hair, the customer decides, I really want a convertible. In the first instance, the customer got exactly what they asked for months prior, because the development team was just following a plan. But in the second instance, the customer got exactly what they desired, because they were working iteratively and interactively with the development team. In the end, you develop something that's a little bit different, but it's closer to what the customer really wants. Giving the customer what they really want is the main purpose of delivering an MVP. A minimum viable product is a tool for learning. It's an experiment to explore the value proposition with your customer. And this experiment may fail, and that's okay, because failure leads to understanding. What did you learn from that failure? What did it teach you? What is the next experiment? What will you do different the next time? These are the questions that lead to gaining knowledge and understanding about what you're building. This is why we use MVPs in DevOps. In this video, you learned An MVP is the minimal thing that you can do to test your hypothesis. An MVP is not about delivery as much as learning. It's okay if the MVP fails. Make sure that you learn from it. After watching this video, you'll be able to define test-driven development, describe how TDD produces higher quality code, describe the red-green refactor workflow, and describe the importance of TDD for DevOps. This is one of my favorite quotes. If it's worth building, it's worth testing. If it's not worth testing, why are you wasting your time working on it? Writing test cases is critical to proving that your code works as intended. What is test-driven development? Test-driven development, TDD, means that your test case drives the design and development of your code. You don't write code and then test it. You write the test cases first. You write tests for the code you wish you had, and then you write the code to make them pass. That may sound counterintuitive. How can I write test cases for code I haven't written yet? Well, how can you write a design for code you haven't written yet? You describe in the design how the code should behave, and then you write the code that behaves that way. TDD is no different. The test case describes the behavior that you want the code to have. This keeps you focused on the purpose of the code. That is, what's it supposed to do? You should absolutely be able to specify that before you start writing any code. Otherwise, how do you know what to write? This is also what keeps you focused on the clients that will call your code. I do a fair amount of back-end development. I love creating services for others to use. And one day, I'm creating what I'm sure would be an awesome service with a great application programming interface, right? A great API. I was down in the bowels of the code and I needed some information, and so I added it as a parameter to the API. And then I needed something else, and I added it as another parameter to the API. And eventually I needed more things, so I added those as parameters too. Now it's time to write some test cases for my code. And at the time, I wasn't following TDD. And when I started writing test cases, I suddenly realized I didn't have half the information that my parameters required. My beautiful API was horrible. How could it be this bad? Where had I gone wrong? Well, I didn't take the caller of my code into account because I wasn't following TDD. TDD gives you the caller's perspective. It allows you to explore how you would want to call the code before even writing it. It makes you consider, what do I know as the caller? What can I pass in and get back as an answer? Having this perspective is critical to writing good code. Code is of no use if no one can call it. So why don't developers write test cases? I get these excuses all the time. The first excuse, I already know my code works. Yes, but others who work on your code in the future won't know if they broke something, including the future you. I tell programmers, whenever you clone and pull from a repo, the first thing you do is run the test cases. How else do you know if you broke something or it was broken before you changed it? Test cases give you the baseline so that other people know that the code is still working. Another one is, I don't write broken code. Well, maybe you don't write broken code, but the environment is constantly churning underneath you. Vulnerabilities are being patched, new libraries are being upgraded, so your code may no longer work. Someone will say something like, we have a vulnerability in Apache Struts library. Can we update it on all our servers? And unless you have test cases to test your code and make sure that it works with a new version of that library, you probably shouldn't do that. And not doing that, as you may know from vulnerabilities that have happened at Equifax, could be catastrophic. You have to write test cases so that you can say with confidence, let me run the test suite. Yes, the new version of Struts works fine. Deploy it to production. My favorite excuse, I have no time. Well, this is the worst excuse because testing actually saves you time in the end. The time you spend writing a few test cases now is going to save you hours and hours of debugging later. Trust me on this one. You don't know who's going to use your code in the future, and you want to make sure your code is solid. TDD will keep you writing solid code. This is the TDD workflow. You write a failing test case, right, for the code you wish you had. Then you write just enough code to make it pass. It doesn't have to be perfect. It doesn't have to be pretty. It does have to make the test pass though, right? Then you refactor the code to make it better and increase the quality. And finally, you repeat the process. This is known as red-green refactor. Many of the testing tools follow this scheme. These tools output failing test cases in red, passing test cases in green, and this is how the red-green refactor got its name. So why is TDD important to DevOps? Well, first and foremost, it saves time when you're developing. As you add new features to the code, or changes to existing features, right? This test case will quickly let you know if something broke. It allows you to code faster because you're more confident. You don't have to worry about if a change just broke your code or broke something, right? When you refactor the code, you can move faster because you know the test cases will catch any changes in behavior. And TDD ensures that the code is working as you expected. If you write the test cases first to define the behavior you want, you will know that you have achieved that behavior when the tests pass. It also means that future changes don't break the code. Failing test cases will instantly alert you that someone has introduced something that broke the code. Finally, and most importantly, in order to create a DevOps pipeline, a CI/CD pipeline, all tests must be automated unless you want to push bugs to production faster. A lot of companies don't understand this. They want to automate using continuous integration and continuous delivery. Without automating their tests, unfortunately, you can't have a CI/CD pipeline without automating your tests. In this video, you learned that TDD means test case drives the design and development of code. TDD allows you to develop faster and with more confidence. The red-green refactor workflow has to do with red is fail, green is pass, and it increases the quality of the code. And in order to create a DevOps CI/CD pipeline, you must first automate your testing. After watching this video, you'll be able to define behavior-driven development, explain how BDD can drive customer expectations, and describe the key benefits of BDD. Behavior-driven development, as its name implies, focuses on the behavior of the system as observed from the outside in. This is different from test-driven development, which focuses on the minutia of how the system works inside. BDD is great for integration testing to see if all the components are behaving together. It forces you to think from the outside in. In other words, you implement only those behaviors that contribute most directly to business outcomes. One of the advantages of BDD is that it describes behaviors in a single notation which is directly accessible to domain experts, testers, developers, and customers. This improves communications across the team. If we compare BDD to TDD, we see that they're coming from the opposite directions. BDD describes the behavior of the system from the outside in. It's looking at the system as a consumer of it would. While TDD tests the functions of the system from the inside out. It's making sure that each component is working correctly, while BDD is making sure that they all work together at a higher level. Put another way, BDD is ensuring that you are building the right thing. Do you have the right set of capabilities in these behaviors? TDD is ensuring that you're building the thing right. Does each feature perform the task that it was intended to? The workflow starts with developers, testers, customers exploring the problem's domain and collaborating to produce concrete examples that describe the behavior they want. They document these behaviors using a language known as Gherkin. It's a natural language representation that I'll talk about in a moment. Next, the team uses a BDD tool like Behave or Python or JBehave for Java or Cucumber for Ruby to run these examples as automated acceptance tests. As the team works on the solution, the BDD tool tells them which examples are implemented and working and warns them about ones that aren't. Before you know it, you have one document that is both the specification and the tests for your software. Gherkin is an easy-to-read natural language syntax that uses a familiar given, when, then syntax. Gherkin is easily understandable by both technical and non-technical people, and if you're wondering where the name Gherkin came from, the original tool that used this syntax was called Cucumber, and Gherkin is a pickle, and pickles are made from cucumbers. Tools have a funny way of producing funny names like that. Here's how the Gherkin syntax is used. Given some context, this is setting up the context or the precondition that sets the stage for the test. The purpose is to put the system in a known state before the user or external system starts interacting with it. when some event happens. This is the principal action or actions that describe what's being performed. This is what takes you from the initial state to the new observed state. Then some testable outcome or behavior is validated. Then is used to observe the outcomes. The observation should be related to the business value or the benefit of the feature. And is used for continuations. Given this and that, then this and that, and so on. It gives you a natural way of adding more context events or outcomes. Let's look at an example from a retail store. These are called feature files or feature documents, and you'll have one feature per document and many scenarios describing this feature. There's only one scenario in this example, but there could be, certainly more to cover all the permutations. This feature is called returns go to stock, and this feature is described by the behavior of the system when a customer returns an item that they have purchased. Notice it uses the as a, I need, so that syntax. We use this in writing our user stories. You could think of this as a user story with acceptance criteria, where the acceptance criteria are the scenarios. This first scenario is called refunded items should be returned to stock. It reads as follows. Given that a customer previously bought a black sweater from me and I have 3 black sweaters in stock, when they return the black sweater for a refund, then I should have 4 black sweaters in stock. It's fairly straightforward. Your stakeholders should be able to look at this and say, yes, this is how return items to stock works. Or maybe, here's another way it could happen. Then you would document a new scenario for the returns go to stock feature. The point is, your stakeholders are actually helping you define the behavior of the system in a formal syntax that you can now execute test cases against. Let me say that again. You can actually execute test cases against this document. BDD tools like Behave and Cucumber can consume this document with no further editing or manipulation and execute test cases to prove that the system does indeed exhibit the behavior. That will put a smile on your developer's face. This is why I add acceptance criteria to every user story. I use the Gherkin syntax to define the acceptance criteria in the user stories that we write. There's no arguing over the definition of done at the end of a sprint. It's indisputable. The code either does or does not exhibit this behavior. BDD improves communication among the team members, like developers, testers, product owners, and other stakeholders. It leads to more precise guidance on how the system should behave. It does this by providing a common syntax that's close to everyday language and has a shallower learning curve compared to TDD tools. Tools targeting the BDD approach generally afford the automatic generation of technical and user documentation from the BDD feature specification. Having a clear behavior visibly results in higher quality code, which reduces the cost of maintenance and eliminates the risk. Finally, with BDD acceptance criteria, you're already converted to user stories and test case scenarios before the actual development. Thus, automating test cases can start creating test process even before the product is tested. In this video, you learned that BDD focuses on the behavior of the system from the outside in. It looks at the system as a consumer of it. BDD uses an approachable syntax that everyone can understand. Key benefits of BDD include improving the communications, a common syntax, and acceptance criteria for user stories. After watching this video, you'll be able to recognize the importance of embracing failure, explain the importance of quick recovery from failure, describe how retry patterns, circuit breaker patterns, and bulkhead patterns help make applications resistant to failure, and describe chaos engineering. Once you design your application as a collection of stateless microservices, there are a lot of moving parts, which means there's a lot that can go wrong. Services will occasionally be slow to respond or even have outages, so you can't always rely on them being available when you need them. Hopefully these incidents are very short-lived, but you don't want your application failing just because a dependent service is running slow or there's a lot of network latency on a particular day. This is why you need to design for failure at the application level. Since failure is inevitable, you must build your software to be resistant to failure and scale horizontally. We must design for failure, We must embrace failure. Failure is the only constant. We must change our thinking from moving to how to avoid failure to how to identify failure when it happens and what to do to recover from it. This is one of the reasons why we move DevOps measurements from mean time to failure to mean time to recovery. It's not about trying not to fail. It's about making sure that when failure happens, and it will, you can recover quickly. Application failure is no longer purely an operational concern. It's a development concern as well. For the application to be resistant or resilient, developers need to build that resilience right in from the start. And because microservices are always making external calls to services that you don't control, these services become especially prone to problems. Plan to be throttled. You're going to pay for a certain level of quality of service from your backing services in the cloud, and they will hold you to that agreement. Let's say you pick a plan that allows 20 database reads per second. When you exceed that limit, the service is going to throttle you. You're going to get a 429 too many requests error instead of a 200 OK, and you need to handle that. In the case, you would retry, right? In this case, this logic needs to be in your application code. When you retry, you want to back off exponentially when it fails. The idea is to degrade gracefully. If you can, cache where appropriate so that you don't always have to make these remote calls to these services if the answer is not going to change. Now, there are a number of patterns that are important strategies, very important strategies to help you make applications resilient. I just want to go over a few of the popular ones. The first one is the retry pattern. This enables an application to handle transient failures when it tries to connect to a service or a network resource by transparently retrying and failing the operation. I've heard developers say, you must deploy the database before you start my service, right? Because it expects the database to be there when it starts. That is a fragile design, which isn't appropriate for cloud-native applications. If the database is not there, your application should wait patiently and then retry again. You must be able to connect and reconnect and fail to connect and connect again. That is how you design robust cloud-native microservices. The key here is the retry pattern, to back off exponentially and delay longer in between each try. So instead of trying like 10 times in a row and overwhelming the service, you retry, it fails. And you wait a second, you retry again. Then you wait 2 seconds. Then you wait 4 seconds. Then you wait 8 seconds. Each time you retry, you increase the wait time by some factor until all the retries have been exhausted, and then you return an error condition. This gives the backend service time to recover from whatever's causing the failure. It could be just a temporary network latency. The circuit breaker pattern is similar to the electrical circuit breakers in your home. You've probably experienced circuit breaker tripping in your house. You may have done something that exceeds the power limit of the circuit, and it causes the lights to go out. That's when you go down to the basement with a flashlight, right? And you reset the circuit breaker to turn the lights back on. Well, the circuit breaker pattern works in the same way. It's used to identify a problem and then do something about it to avoid cascading failures. A cascading failure is when one service is not available and it causes a cascade of other services to fail. With the circuit breaker pattern, you can avoid this by tripping the breaker and having an alternate path return something useful until the original service recovers and the breaker closes again. The way it works is that everything flows normally as long as the circuit breaker is closed. The circuit breaker is monitoring for failure up to a certain limit. Once it reaches that limit threshold, right, that certain threshold, the circuit breaker trips open and all further calls to the circuit breaker return with an error, without even calling the protected service. And then after a timeout, it enters this half-open state where it tries to communicate with the service again. If it fails, it goes right back to open. But if it succeeds, it becomes fully closed again. The bulkhead pattern can be used to isolate failing services to limit the scope of a failure. This is a pattern where using separate thread pools can help to recover from a failed database connection by directing traffic to an alternate thread pool that's still active. Its name comes from the bulkhead design on a ship. Compartments that are below the waterline have walls called bulkheads between them. And if the hull is breached, only one compartment will fill with water. The bulkhead stops the water from affecting the other components, the other compartments, right, and sinking the ship. So using a bulkhead pattern isolates the consumers from the services as cascading failures by allowing them to preserve some functionality in the event of a service failure. Other services and features of the application continue to work. Finally, there's chaos engineering, otherwise known as monkey testing. While not a software design pattern, it's a good practice to prove that all your design patterns work as expected under failure. In chaos engineering, you deliberately kill services to see how other services are affected. Netflix has a suite of failure-inducing tools called the Simian Army. Chaos Monkey solely handles termination of random instances, and Netflix randomly kills things to see if they come up and whether the system will recover gracefully. You cannot know how something will respond in a failure in production until it actually fails in production, so Netflix does this on purpose. All of these patterns can help you build more robust software and respond gracefully to intermittent failures. In this video, you learn that failure is inevitable, so we design for failure rather than trying to avoid failure. Developers need to build in resilience to be able to recover quickly. Retry patterns work by retrying failed operations. Circuit breaker patterns are designed to avoid cascading failures. Bulkhead patterns can be used to isolate failing services, and chaos engineering is deliberately causing services to fail to see how other services are affected. After watching this video, you'll be able to recognize the benefits of working DevOps, describe how Taylorism is not beneficial for software development, and recognize that software development is more like craft work than factory work. In order to change your culture, you must change the way that people work. Working DevOps is all about facilitating a culture of teaming and collaboration. It's right from the Agile Manifesto. We value individuals and interactions over process and tools. Establishing Agile development as a shared discipline is at the core of building a strong DevOps culture. You also want to automate relentlessly to enable rapid DevOps responses. Sometimes automation is all people think about when they think about DevOps, but DevOps is not just about automation. But in order to respond rapidly, you must automate. Building a culture in which doing tasks manually is frowned upon and automating tasks is rewarded is the culture you want to have. Pushing smaller releases faster so that you can measure and remediate impact is also extremely important. We want fast feedback loops, and one way to achieve that is with frequent, smaller releases. This minimizes risk and maximizes learning. The problem we're up against here is that we've been working the same way since the Industrial Revolution. This is known as Taylorism. Taylorism is named after a U.S. industrial engineer, Frederick Winslow Taylor, and his 1911 book, Principles of Scientific Management. Taylor laid down the fundamental principles of large-scale manufacturing through assembly line factories. During the Industrial Revolution, Taylor established the adoption of command and control management, which has become the dominant method of management in the Western world. He also prescribed that organizations be divided into independent functional silos. Taylor watched how workers executed their jobs and realized that if workers were separated into task-specific roles, they could gain greater efficiency. This assembly line concept grew from this, right? For example, workers would just put on the doors of the cars, and the next worker would just put on the windows, and so on down the line. And this was faster than one worker tooling up to put on a door, then retooling to put on a window, and then tooling up for each stage of the assembly. One of the impacts of Taylorism that we see in business today is this idea of decision-making separated from work. In other words, managers do all the planning and decide what the workers should do, and the workers mindlessly do the tasks. They are told what to do. Many projects are still managed this way today. You can see the impact of Taylorism on information technology today. We have project management that is at the top of command and control food chain. Project managers give the directions. Architects design the systems and hand off to the developers to code. Developers hand off to testers. Testers hand off to operations. Operations hands off to security. Each performs a task-specific role in their own silo, with each handoff being an opportunity to make mistakes, lose context, or cause bottlenecks. Optimized roles may work well for making cars on an assembly line. It does not work well for software development. Automobiles are made up of standard parts. In software development, most of the parts don't even exist yet. If they did, we'd buy them off the shelf. The fact that we have to write the code ourselves illustrates that this is bespoke. This is customized or specialized. Software development is considered knowledge work. It's also craft work when you think about it. is creating a one-of-a-kind application that doesn't exist yet. When you make automobiles, you tool up to make hundreds or thousands of them. That makes the rigor of tooling worthwhile. In software development, you're making one application. Why would you tool up an entire assembly line to make one of something? It doesn't make sense to treat software development like a factory assembly line. Steve Jobs once said, "It doesn't make sense to hire smart people and then tell them what to do. We hire smart people so they can tell us what to do." Managers need to be able to trust that they've hired the right people, let them know what needs to be done, and then get out of their way and let people amaze them. To fully work DevOps, you must abandon command and control management, abandon Taylorism. To be DevOps, teams must stop working in silos and work together with a common goal. All the handoffs that silos cause will only slow them down. In this video, you learn that working DevOps means pushing small releases faster in order to gain feedback, minimize risk, and maximize learning. Taylorism was designed for factory work, while software development is like craft work. And handoffs created by working in silos results in mistakes, bottlenecks, and delays. After watching this video, you'll be able to recognize that software engineering is different from civil engineering, describe how software engineering is constantly changing, and describe how the project management model does not work well for software development. A common practice that goes against work in DevOps is treating software engineering efforts as if they were civil engineering projects. For a civil engineering project, you might want to build an office building. So you hire an architect who designs the building and creates a blueprint. The blueprints are handed off to the construction team who follows the blueprints to build the building. Once that handoff is made, the architect moves on to the next project. They may get consulted on some questions about the blueprint, but largely their job is done and they move on. The construction team spends months building the building to the specifications laid out in the blueprints. When the construction is complete, the building's handed off to the maintenance team, who then takes over maintenance of the building. And unless you're in California, the ground doesn't move too much from under the building, and things are fairly steady from that point forward. The problem is, we treat building software the same way. Software development efforts are usually run as if they're civil engineering projects. We view it as a project to be completed and then move on. Architects throw designs over the wall to the developers, and they move on to the next project. Developers throw code over the wall to the testers, and when the project is complete, the whole thing gets thrust over the wall, right, to the operations team to run and maintain it as part of business as usual effort. All the people on the project team get reallocated to new work, and maybe a skeleton development team is left for maintenance. In contrast to this civil engineering approach, software engineering is organic. The software stack under your application is constantly changing, even when the application doesn't. The operating systems are being patched, packages are being updated because of newly discovered vulnerabilities. Right? These changes affect the application. And the operations team has to deal with all these changes on their own. New features are constantly being added. Once an office building is built, you usually don't add new floors. Software is not like this. The behavior of the system is constantly changing. Yet we continue to treat software engineering as if it were a civil engineering project. The project model is fundamentally flawed as a way of doing software development. When a project is complete and people move on, there's no ownership. This is not the way to create great software. You want to treat software development like product development instead. Products have long lives and continue to be enhanced. If instead of moving on, the same team builds and maintains the software, they'll retain a deep understanding of the code and feel ownership for the code. They'll have great ideas on how to make the code better. We must stop treating software engineering like civil engineering projects. In DevOps, we want stable, long-lasting team membership with end-to-end ownership. This is how to create great software. In this video, you learned that software development is often viewed as a project to be completed and then passed on to operations to maintain. Software engineering and the behavior of the system are constantly changing. And team ownership and stable teams make software development more like product development and less like project management. After watching this video, you'll be able to differentiate between traditional ops and DevOps, describe ways Dev and Ops view each other, and list required DevOps behaviors. DevOps presents diametrically opposed views to how traditional enterprises think. Enterprises are built around end-to-end processes that see new as complex, high risk, and expensive and time-consuming. They approach anything new as a one-time project to be completed in a fixed time frame for a fixed budget and then move the people on to the next project. DevOps seeks to turn this on its head, breaking big projects down to deliver a continual series of small changes that are more manageable. Smaller changes to be completed with less risk, so DevOps reduces the risk of large projects. The catch is that small changes cannot survive the traditional overhead that enterprises add to everything you want to do. Processes like change review boards don't work in DevOps because they cannot move at the speed of need for small changes. We have a clash of work cultures between traditional ops and DevOps. In traditional ops, we make manual configuration changes to critical infrastructure. In DevOps, we automate deployment to all environments. This is why traditional ops needs change review boards. Everything is done manually, and humans are fallible, and even if the change is approved, there's no guarantee that it will be implemented correctly. In traditional ops, application architecture is defined by the network design. In DevOps, it's the other way around. The network design is defined by the application architectures. We have software-defined networks that conform to whatever the architecture needs. In traditional ops, bespoke infrastructure is built once and then maintained forever. In DevOps, ephemeral infrastructure is created for new deployments. We don't maintain the infrastructure. We tear it down and replace it entirely. You can't do this unless everything is automated. The manual overhead would slow you down too much. In traditional ops, risk is managed through change windows. Changes are only made at certain times, pre-designated as change windows. That is, no change can happen outside those change windows. In DevOps, risk is managed through progressive activation. We can make a change to the system at any time. We use deployment techniques to activate or deactivate the change as needed. And finally, traditional ops has process bias towards build once. Traditional ops builds everything manually and maintains it forever, or at least until it's not needed anymore, which is usually several years. Sometimes they build it once and can't figure out how to build it again the same way because the build wasn't documented. In DevOps, processes are re-engineered for high volume, rapid throughput of changes, making builds repeatable, leveraging infrastructure as code to ensure that anything we do can be built again. When cultures clash, it's a no-win scenario. Development is measured by how much innovation developers can produce. They keep up with the changing needs of the users by developing and deploying new enhanced capabilities. Operations want stability. They want to ensure that users can use those services and applications and that their data and information are kept safe. These two goals are in opposition. You can't have both. Andrew Clay Schaefer called this the wall of confusion that exists between dev and ops. What we need to do is break down that wall. The first step is to change the way development operations view each other. Ops, well, the ops view of development is that development is throwing dead cats over the wall. They manually implement changes that lack of backup plans, lack of testing. Their environments don't look like production environments. And then the devs, they think ops are making these all or nothing changes in the dead of night, in these change windows, and they're the furthest from the code, so they don't understand. Ops is using cut and paste from run books, right, from Word documents. Silos breed apathy. You can't have people working in two silos with diametrically opposed metrics. It's never going to work. You must bring these people together. You must give them one set of metrics that add value to the customer. The website works, developers get the praise. The website's down, ops gets the blame. Did I mention the no-win scenario? This is not a healthy working environment. Here is some required DevOps behavior. DevOps turns a number of these things on their head. You need to break down the organizational silos and the handoffs that they cause and move to a culture of shared ownership and high collaboration. There's no hole on your side of the boat. Everyone must see themselves as in this together for a common goal. You must go from fear of change to managing risks by embracing change, managing changes that are small. Big changes are always scary to everyone. Make the changes small and manage the change. Go from building something once, these handcrafted snowflake servers where each one is unique and you could never find another one just like it, to using ephemeral infrastructure deployed using infrastructure as code techniques so that they are repeatable. Every time you build a Docker container, every time you build a virtual machine, build it exactly the same. If you did not change the code, it will be built exactly the same and get the same results. Change from manual fulfillment, ticket queues, and people manually doing things to enabling automated self-service. I've seen companies adopt the cloud and then put a ticket queue in front of it so that only the IT people can provision from the cloud. That defeats the whole purpose of having self-service cloud. Self-service is the way to move quickly. And finally, you must change from alarms and callbacks and escalations to fast feedback loops that are data-driven. And make sure you can get that information about what's going wrong in production and then react to it when you need to. These are the behaviors that must change in order for you to fully become a DevOps organization. In this video, you learned that enterprises see change as complex and time-consuming. DevOps breaks big projects into a series of small manageable changes. Traditional ops builds once and maintains, and DevOps ephemeral infrastructure is created for each new deployment. Dev wants innovation, while Ops wants stability. Required DevOps behaviors include shared ownership, collaboration, embracing change, and data-driven responses. After watching this video, you'll be able to define infrastructure as code, describe ephemeral infrastructure, and describe immutable delivery via containers. Infrastructure as code is the practice of describing infrastructure in textual format. I'm not talking about documentation here. I'm talking about a textual format that is executable, otherwise known as code. You want to be able to configure your infrastructure using a textual description that you can give to a tool to execute. The tools that make this possible are called configuration management systems. These are tools like Ansible, Puppet, Chef that allow you to describe your infrastructure as code and then create that infrastructure and keep it in that state. You never want to perform system changes on software configurations manually. This is not reproducible and it's extremely error-prone. You want to use templates and scripts that describe how to install and automatically configure elements such as systems and devices and software and users. Then you can take that textual code and store it in your version control system so that you have a history of all the changes. This way, everyone knows which version is the latest version and how the infrastructure should look. Technology like Docker and Vagrant and Terraform and even Kubernetes also allow you to describe your infrastructure as code, and this code should be checked into version control. The reason this is so important is because server drift is a major source of failure. Over time, servers get updated for various reasons and not always by the same people. This causes them to drift from their original configuration. Sometimes the accumulation of these changes cause failures in unpredictable ways. Even worse is having servers that are supposed to be the same, but one of them keeps failing due to a misconfiguration somewhere. The saying, servers are cattle not pets, refers to how you treat servers. Suppose you have 1,000 head of cattle. You don't take the time to give each one of them a name. When one of them gets sick, you put them out of their misery and you replace them with another. Pets, on the other hand, they're lovingly cared for and nursed back to health when they're sick. The message is not to lovingly handcraft servers or spend too much time debugging when they don't work. You want to be able to replace them with an identical server that is working properly. That means you must think about your infrastructure as something ephemeral or transient. It only exists for the time that you need it, and then you remove it when it's not being used. For example, in the past, building test environments took weeks, so you would keep them around for months because it took weeks to build them. But when you have infrastructure as code, it takes minutes to deploy a new set of servers. So you could bring up a test environment and use it for a period of time and then destroy it. If you need it again another day, create a new one. You don't keep it running forever. You just bring it up when you need it. You bring it down when you no longer need it. It's transient. This also allows us to release through parallel infrastructure. For example, I can build up a server that looks just like the one that's in production, and I could deploy a new version of an application or monitor it to see if it's working correctly. And if it looks like it's behaving correctly, I shut down the one in production, I make the new one the production server. With parallel infrastructure, I can keep things running constantly. Infrastructure as code allows me to create identical infrastructure every time. Ephemeral infrastructure can be used and then discarded because servers are built on demand via automation using infrastructure as code techniques. Tools such as Docker help us create immutable delivery. Docker is a packaging technology that allows us to bring things up and bring them down in a consistent fashion in an isolated environment called a container. Docker supports infrastructure as code by allowing you to specify how to build the image from code called a Docker file. These Docker files build the same image in the same way every time. Docker then creates a container from that image in the same way every time it's deployed. This means that the container is not the one that's running in the production, right? Can run on the developer's laptop. It's the ultimate dev prod parity. This is because all of the dependencies to run the application are packaged together inside the container. This limits any variance or possible side effects. There's nothing else needed except for the container runtime like Docker to run it on. Tools like Docker also allow you to do rolling updates with immediate rollback, right? You're not installing the application to see if it works and then uninstalling it if it doesn't. You simply bring up a Docker container with the new version. If it starts misbehaving, you stop it and bring it down, bring up the previous version, which is already installed in its own container. It literally takes seconds. You would treat containers that start misbehaving the same way. You delete the container, you create another one that take its place. The new container is going to be exactly like the old one on the first day it came up. If there's some kind of corruption, it's going to be clear that the corruption brings the whole thing back down to its original state. This is a different way of working. You never make changes to running containers like you would a running server. Remember, cattle, not pets. You don't patch containers for vulnerabilities or modify them in any way. To make any change, you make a change to the image that the container was created from. Then you redeploy the new container to take the place of the old one. The reason is simple. If you patch a container and it dies, the new one is brought up to take its place, the new container won't have the patches. That's why it's imperative that you modify the image, right? They are the template for creating the containers, and they are the things that must be kept up to date, not the running containers. In this video, you learned that infrastructure as code describes infrastructure in an executable textual format. Ephemeral infrastructure can be used and then discarded. Servers are built on demand via automation. Rather than patching a running container, immutable delivery is making changes to the container image, then redeploying a new container. After watching this video, you'll be able to describe continuous integration and continuous delivery, explain the reason for using small batches in continuous integration, and describe the benefits of continuous integration. People use the acronym CI/CD as if it's one thing, but continuous integration and continuous delivery are two separate and distinct practices. Continuous integration, CI, is the process of continuously building and testing and integrating every developer change into the master branch after a set of tests have passed. The result is potentially deployable code. Continuous delivery, CD, is a series of practices designed to ensure that code can be rapidly and safely deployed to production by delivering every change to a production-like environment. Notice that I said production-like. It doesn't have to be deployed into production, and in fact, many people reserve the term continuous deployment for when you're deploying continuously into production. For continuous delivery, you just have to deploy it somewhere like development, test, staging environment that mimics the production environment. For example, if the production environment is containers running on Kubernetes, you should deploy to a development environment in containers on Kubernetes. Let's start by looking at how traditional development is done. Developers work in long-lived development branches. Typically, they do it this way because older version control systems made a complete copy of code whenever you made a branch. So making branches was very expensive. The cost causes people to resist making branches, and when they do, they don't delete them very often. But with modern version control systems like Git, this is no longer the case. But some development teams have kept the traditional practice. These development branches are kept separate from the release branches and periodically merged into a release branch, but not without lots of breakage. This is because the amount of changes made over a long period of time make the branch more vulnerable to merge conflicts. Builds are run periodically, sometimes nightly, on the release candidate branch. Developers continue to add to the development branch, which drifts further and further from the master release branch. In this scenario, it may take days to merge the code to get it back working. In contrast, continuous integration is a development practice that requires developers to frequently integrate code into a shared repository. And by frequently, I mean daily if possible. This is accomplished by having developers work in short-lived feature branches that are merged into the master once the feature is complete. This means you integrate each feature as it is completed. You don't wait until a long list of features are complete before you integrate them. Each check-in is then verified by automated testing and automated build, allowing teams to detect problems early and often. Once merged, the branch is then deleted and a new branch is created for the new feature. Working in small batches helps accomplish continuous integration. By committing regularly, every developer can reduce the number of conflicting changes because less time has passed between merges. The more time that passes, the greater the risk of merge conflicts. Working for a week on code and then checking it all in at once increases the risk that the new features will conflict with other features. These conflicts can be difficult and time-consuming to resolve. Using pull requests allow team members to communicate about the change they're making. Every pull request is an opportunity for a code review so that other developers review the code. This ensures that all the code is being looked at by more than one person and lowers the risk of something going wrong. Committing all changes at least once a day or once per build is generally considered part of a definition of continuous integration. Speaking of pull requests, every pull request should be built and tested. This should happen automatically. The system should build the changes of the current working version to verify that the integration works correctly. A common practice is to use automation in which a CI tool monitors the version control system and then automates and runs the build automatically. Most CI tools like Travis CI, Circle CI, Jenkins, GitHub Actions, they all have the capability to monitor your version control system for changes as well as automate the build process. Once the code is built, all tests should be run to confirm the code behaves the way the developer expected it to. In other words, make the build self-testing. The test results should feed back to the pull request, and you should never merge a pull request that is failing tests. One of the benefits of practicing continuous integration is that you can get faster reaction times to the changes, and you can move faster. So you can move faster because your tests are automated. Since the tests are automated, you know that everything you've done up to that point has been tested and known to work. If you have these tests run automatically, you're not wasting time testing. You're spending your time building features. CI reduces the risk of integrating code because you're integrating smaller changes. When things change less, there's less risk of breakage due to changes. Submitting pull requests puts more eyes on the code and therefore results in higher code quality. Everyone has input on the quality of the code. And finally, you know that the code that's in version control works. Remember, the master branch should always be deployable. I've had students ask me, can I write the test case after I build the user interface? And I tell them, by that time it's too late. You've committed the user interface to the master branch. And if we need to deploy the master branch, we have no idea if the user interface works. You should assume that code that has not been tested does not work. You should never merge untested code into the master branch. The master branch should always be deployable. In this video, you learned that continuous integration is building, testing, and integrating every change into the master branch after tests have passed. Continuous delivery ensures that code can be rapidly and safely deployed to production by delivering every change to a production-like environment. Working in small batches aids continuous integration by reducing the number of conflicting changes. The benefits of continuous integration include faster reaction time, moving faster, and reducing the risk of integrating code. After watching this video, you'll be able to describe a CI/CD pipeline, define continuous delivery, list the 5 key principles of continuous delivery, define continuous deployment, and describe how DevOps manages risk. Martin Fowler defines continuous delivery as a software development discipline where you build software in such a way that the software can be released to production at any time. That's easier said than done. Let's start with what Fowler means by in order to be able to release to production at any time. It means the master branch should always be deployable. In order to do that, you need to build and test every change. Building and testing every change is the definition of continuous integration. So continuous delivery requires continuous integration. This may be why people simply say CI/CD like it's one word, because you need continuous integration in place before you can implement continuous delivery. You need a way to know if something will break the build. One way to accomplish this is by delivering every change to a production-like environment. It doesn't have to be the actual production environment, but it should be enough like it so that the same procedure can be used to deploy to production. Along the way, there are automated gates that create a pipeline of checks, such as unit testing, integration testing, quality checks, vulnerability scans, security tests. These tests ensure the quality of the code. When this is all set up, we refer to it as a CI/CD pipeline. Like a pipeline, it's a set of tools where the output of one feeds the input of the other. Let's talk about what's needed to set up a CI/CD pipeline. To start off with, you need a code repository to host and manage all your source code. That's the starting point that initially feeds the pipeline. Then you need a build server to build the application from source code. Most cloud-based CI/CD tools like Travis CI, GitHub Actions provide this for you. Then you'll need an integration server / orchestrator to automate the build and run the quality and other tests. Most cloud-based CI/CD pipelines like IBM Cloud Continuous Delivery will provide an orchestration capability for you. You'll also need an artifact repository to store binaries, the artifacts of the application. This is where your Java jar files and war files, Python wheels, Ruby gems, Docker images, or whatever compiled artifacts have been tested and proven to work. And then finally, you'll need a tool for automatic configuration of your deployment environment. Again, most cloud-based CI/CD pipeline tools will provide a way to automate your deployment. When we overlay continuous integration and continuous delivery on top of the software development lifecycle, we can see that plan, code, build, and test are part of continuous integration, and release, deploy, and operate are part of continuous delivery. These are the two cycles, CI and CD, that feed each other. There are 5 key principles that are at the heart of continuous delivery. The first is built-in quality. The CI/CD pipeline comes into play here because it allows every code change to go through a set of rigorous checks to ensure high code quality. The second principle is working in small batches. Working in small batches is important because smaller changes are easier to test and represent less risk of something getting broken. The third is important to acknowledge that computers are good at performing repetitive tasks, but people, not so much. People are good at solving problems. It's best to automate the repetitive tasks using computers and then leave the problem solving to the people. The fourth key principle is to relentlessly pursue continuous improvement. We should always be looking for ways to improve. That means we need to measure using actionable measurements and then take action when the measurement shows what we can improve. And then finally, the fifth principle is that everyone is responsible. When a build is broken, it's everyone's responsibility to help fix the build. Broken builds hold back everyone from moving forward. I wanted you to be aware of the term continuous deployment. I wish they had called it continuous release to distinguish it from the initials of continuous delivery. Continuous deployment is reserved for deploying to production. You can see by the graphic how continuous integration covers pushing code to version control and automating the build and testing once it's integrated. Then continuous delivery takes over using the artifacts from the build and automatically deploys them to some environment. When we use automation to deploy to production, then it's referred to as continuous deployment. Right about now, you might be thinking to yourself, all this automation sounds risky. How do you manage that risk? DevOps manages risk by increasing the rate of change rather than avoiding change. It sounds counterintuitive, but here's how it works. In DevOps, deployment is king. Deployment should be painless. You want to deploy early and often. The idea is to build up muscle memory. You deploy your code several times before it goes to production. You deploy it to a development environment. You deploy it to a test environment. You deploy it to a staging environment. You might deploy it to a pre-production environment. Since these deployments are automated, by the time you deploy it to production, you know that it works. It would be unusual for it not to work because computers are really good at repetitive tasks. This is why you don't want humans involved in doing manual steps. Once you automate deployment, the code is going to go to production the same way every time. The second notion is that deployment is decoupled from activation. This may sound strange, but you can deploy code with something called a feature flag. Feature flags turn your code on and off without having to redeploy. You can deploy a feature, turn it on, see how it works. If it's not working, turn it off. Or if it's not ready, turn it off until it's ready and then turn it on in production. Feature flags have become very popular for decoupling deployment from activation. You can also do waves of activation using blue-green deploys and canary testing. This is where you deploy a new feature, but only send 10% of your traffic to it and monitor if it's working properly. Then you can gradually send higher and higher traffic percentages to the new version until you're happy that it's working, and then send 100% of the traffic. Or, if it's not working, you roll it back. This is also known as zero downtime deployment because at no time do you have the system take an outage, right? You don't have to bring it down to deploy new code. Finally, deployment is not a one-size-fits-all. You need to see what works for the product you are building and for what your customer expects. There are many techniques that can be adopted to fit continuous delivery into your business scenario. In this video, you learn that CI/CD pipeline tools provide a way to automate deployment. Release, deploy, and operate are part of continuous delivery. The 5 key principles of continuous delivery have to do with quality, working in small batches, automation, continuous improvement, and shared responsibility. Continuous deployment is when automation is used to deploy to production. DevOps manages risk by increasing the rate of change rather than avoiding it. After watching this video, you'll be able to identify how organizational structure impacts DevOps, to explain Conway's Law, and describe the optimal organization for DevOps teams. Let's take a look at how your organizational structure affects your ability to become DevOps. Part of becoming a DevOps organization is to first become Agile, because Agile is a fundamental tenet of DevOps. You must ask yourself, is the culture of my organization truly embracing the Agile mindset? It's important to remember that Agile teams must be small. If you have large teams and you want to be successful in implementing DevOps, you need to make your teams small. Agile teams should be dedicated. You can't have people committed to several projects and expect all those projects to move at the same speed, or for your people to remain focused on any one project for too long. Agile teams should be cross-functional. What we call the development team includes all the people responsible for developing the product. This means software engineers, test engineers, operations engineers, business analysts, whatever it takes. These people need to be on the same team and not working in silos, getting each other's attention through ticketing systems. These teams need to be self-organized. They commit to work one sprint at a time. Let's look at why organization is important, starting with Conway's Law. Back in 1968, Melvin Conway stated any organization that designs a system defined broadly will produce a design whose structure is a copy of the organization's communication structure. For example, if you ask 4 teams to build a compiler, You get a 4-pass compiler. You should not be surprised you got a 4-pass compiler. You asked 4 teams to build it. If you have a user interface team, and an application team, and a database team, you get a 3-tier architecture. You should not be surprised you got a 3-tier architecture. You asked 3 teams to build it. This is Conway's Law in action. If you want to change the way you build software and adopt a microservice application architecture, you need to reorganize your people around the architecture you expect them to build. In a traditional organization that is organized around technology, you might have a separate user interface team that performs all of the user interface work. Regardless of what feature you're building, you need to get the attention and time of someone on this team to add a user interface element for your feature. This is sometimes called the front-end team. Then you have the application team or the back-end team, and they add the application logic. They don't deal with the front end or things like database schemas because you have a database administrators team to manage all of that. No one touches the database unless they open a ticket to get a database administrator, a DBA, to do the work. When you organize this way, you get a 3-tier architecture. Like I said, you shouldn't be surprised you have a 3-tier architecture. You asked 3 teams to build it. Conway's Law tells us that an organization will produce a design whose structure reflects the organization's communication structure. No surprises here. We got what we organized for. This is why paying particular attention to how you are organized is so important. It's better to organize your teams around business domains. You may have an account team that manages login, registration, and user data. They have user interface skills, application skills, and database skills on a cross-functional team. Then there's the personalization team. They create personalization algorithms using artificial intelligence, and they control their own user interface, their application logic, and their own database. Finally, you might have a warehouse team that is building capabilities around shipping, receiving, and inventory. Those are the microservices that they manage from front to back. The warehouse team doesn't need to coordinate with any other teams to develop their features. They don't need to open tickets to get the attention of other teams to complete their features. They work as a small, dedicated, cross-functional, self-organizing team. If you don't organize around business domains, you are not going to get the full benefit of DevOps. You want to align your teams with the business. Each team should have its own mission aligned with the business domain. Make sure that they have the autonomy they need so that it feels like a mini startup. They need to be self-organized and cross-functional with 5 to 7 engineers, no more than 10. You then want to empower your teams by giving them end-to-end responsibility for what they produce. They commit, build, deploy, maintain, and operate their services. They control everything. And you want them to have a long-term mission, usually around a single business domain. I can't stress enough how important this is when creating high-performing teams. If you have people coming in and out of the team constantly, you will never get the benefits of having a dedicated team with a long-term mission that builds ownership and pride in their work. In this video, you learned that organizations must have small, dedicated, cross-functional, self-organizing teams to successfully implement DevOps. Conway's Law implies that a company's design results are a direct reflection of the company's communication structures. And successful DevOps teams should be organized around business domains. Each team should have a mission that aligns with a business domain. After watching this video, you'll be able to define DevOps, identify misconceptions about DevOps, and recognize the best approach for teams using DevOps. The term DevOps is often misunderstood. For example, this drop-down list that I saw recently while signing up for a webinar, it asked for my job function and provided the options of DevOps/technical ops or software developer/engineer. I'm a software engineer who practices DevOps. These job titles don't reflect DevOps, and frankly, this organization should know better. Clearly, they did not notice the letters DEV in DevOps, which stands for development. Here's a clue. If you're not doing development, you're not doing DevOps. You're just doing ops. They apparently did not understand this. There are both dev and ops in software development. For them, DevOps/technical ops is something that the ops people do. But DevOps is not something that just ops people do. There are different perspectives of DevOps. You start with traditional development and operations that have a wall of confusion between them. Many organizations, like this webinar organization from my example, think that DevOps is something that ops people do, and that DevOps is a subset of operations. Some organizations think that DevOps is something developers do. But most organizations think DevOps is a separate team that sits between dev and ops and keeps both of them happy. I'm going to talk more about that in a moment. None of these perspectives are correct. DevOps is a mindset that the whole organization adopts. You'll see this a lot in startups. DevOps is their company culture. It's dev and ops working together with the same mindset, preferably on the same team, using the same goals and measurements. Jez Humble wrote, "The DevOps movement addresses the dysfunction that results from organizations composed of functional silos. Thus, creating another functional silo that sits between dev and ops is clearly a poor and ironic way to solve these problems. Remember, there's no such thing as a DevOps team. That's an anti-pattern. It causes more problems than it would solve." You see, DevOps is the recognition that working in silos doesn't work. You may have seen this wall of confusion graphic made famous by Andrew Clay Schaefer. It depicts the diametrically opposed goals of development and operations. Development is measured by how many new features they can push to production. Operations, on the other hand, is measured by how stable production is. One way to stabilize production is to not change anything like adding new features. If you create a separate DevOps team, you are just creating another silo that further separates dev and ops. This doesn't make any sense when you look at it this way. You don't create a team to make you DevOps any more than you would create a team to make you Agile. No one forms an Agile team and claims that their organization is suddenly Agile because of that team over there. No, the organization must adopt the Agile mindset, becoming Agile. DevOps is no different. The reality is that DevOps is not a job title. It's not something one person does or a team does. It's a cultural transformation on an organizational scale. It's the practice of development and operations engineers working together during the entire software lifecycle, preferably on the same team, following lean and agile principles that allow them to deliver high-quality software stably and continuously. It starts with learning how to work differently and embracing cross-functional teams with openness, transparency, and trust as pillars. If that doesn't sound like your organization, then you're probably not practicing DevOps. In this video, you learned that DevOps is a mindset that the whole organization adopts. DevOps solves the problems caused by siloed teams. DevOps is the practice of development and operations engineers working together during the entire software lifecycle, following lean and agile principles that allow them to deliver high-quality results. After watching this video, you'll be able to explain the importance of consequences, describe how functional silos lead to apathy, and identify your organizational DevOps objective. Jez Humble, author of the book Continuous Delivery, once said, "Bad behavior arises when you abstract people away from the consequence of their actions." He was referring to the fact that silos abstract people away from the consequence that their actions have on the other silos because they don't see them or feel the effect. One example that Jez cites is a conversation he had with an engineering director. They talked about a company that had a series of quality problems with their software. They didn't have a QA team, so they thought hiring a QA team would resolve the problem. Much to their surprise, the quality actually decreased. One reason for this is because developers felt they were no longer responsible for testing their code. Instead of being focused on quality, they were now focused on getting their features into test as quickly as they could. They figured it's the QA team's job to worry about quality. They abstracted the development team away from the consequence of writing buggy code. When developers stopped testing, the QA team could not manage the increased volume of testing, and the quality of the software actually went down. This is why we say that functional silos breed bad behavior. I personally don't recommend having a QA team. I like making developers responsible for all the tests so they take pride in the quality of the code that they develop. Actions have consequences. Here are 2 things you can do to avoid the problem. You can create cross-functional teams so that everyone is dealing with teammates instead of ticket queues. If you can't create cross-functional teams, then have the developers rotate through the operations so that they can feel empathy for what the operations engineers do every day to keep their application running. You can also have the operations engineers join the developers' stand-ups in their showcases so they can understand what the developers are doing. You can make people responsible by putting developers on pager duty or have them own their service level agreement for the products and services they build. It's amazing. You only have to call a developer once or twice at Sunday at 3 a.m., and they'll start writing better code on Monday. So put them in the on-call rotation. Let them feel the pain of operations, and they will start writing better code. The message is clear. If you abstract people away from the consequence of their actions, they will become apathetic. Your DevOps organizational objective should be to attain a shared consciousness with distributed local control. You want everyone to understand the big picture, where you're going, what you hope to accomplish, but you want to give them local control of how to accomplish it. This empowers people to do their best work instead of waiting for orders from above. As Werner Vogel, CTO of Amazon, said, "You build it, you run it." There is no difference between dev and ops. Everyone is responsible for delivering value to the customer, but you must give them the means to do it. In this video, you learned that actions without consequences can lead to apathy. Allowing teams to feel the effect of their actions fosters empathy, resulting in higher quality work. And your organizational DevOps objective should be to attain a shared mindset and empower everyone to deliver customer value. After watching this video, you'll be able to explain the importance of measuring what you want to improve, identify the value of social and DevOps metrics, and recognize that DevOps changes your approach to problem resolution. How do you change a culture? This is from a paper by Stephen Kerr from the Academy Management Journal back in 1975 on the folly of rewarding for A while hoping for B. Whether dealing with monkeys, rats, or human beings, it's hardly controversial to state that most organisms seek information concerning what activities are rewarded and then seek to do, or at least pretend to do, those things often to the virtual exclusion of activities not rewarded. The extent to which this occurs, of course, will depend on the perceived attractiveness of the reward offered, but neither operant nor expectancy theorists would quarrel with the essence of this notion. You cannot measure for A and hope you get B. It's not going to happen because you get what you measure. So measure what matters. If you measure widget production, you will get lots of widgets. If you measure lines of code, you'll get many lines of code, semicolons all the way down. We used to measure lines of code by the thousands of lines of code, KLOC. Is it good code? I do not know. I do not care. I am measured by how many lines of code I write, so I'm going to write verbose code. Remember, you get what you measure. If you measure people by ranking them against each other, you will get antisocial behavior. A lot of companies do this. They rank people. So let me get this straight. You want me to help my peer, but you are going to rank us against each other. So I help them so that they get the better ranking than me and they get the pay raise or the promotion that I want. Yeah, how does that work? Companies do this all the time and their management doesn't seem to get it. You get what you measure. If you want people to be social, then you must measure them on being social. You should measure developers by their social interactions and sharing of code and knowledge. That is how you get social coders. Here are 2 metrics that I like to use to measure social coders. Who is leveraging the code you are building? Are you building code that the rest of the company or open source community find valuable enough to reuse in their solutions? But that's only half the puzzle. That will get people thinking about how can they make their code valuable to others. But you need the second metric. Whose code are you leveraging? Are you wasting all of my development dollars reinventing wheels? Or are you leveraging the existing wheels and only building the bespoke parts that don't exist? Both of these metrics are needed because they incentivize both sides to share their code and reuse each other's code because you get what you measure. You need a social metric to get social behavior. DevOps is all about continuous improvement. That means that you must know where you are coming from in order to measure if you're going in the right direction. It starts with taking a baseline. What do you want to improve? Maybe it currently requires 6 team members, 10 hours to deploy a release of your product. Maybe it costs X dollars for every release. Whatever that measurement is, that's the baseline. Then you need to create a goal. Metric goals allow you to reason about these numbers and judge the success of your progress. Perhaps you want to reduce deployment time from 10 hours to 2 hours. That's a very achievable goal. Your baseline determines it takes 10 hours, so you aim for a threshold of 5-fold improvement to 2 hours. Or maybe you want to go from needing 6 team members to 1 team member. Or maybe you want to reduce the number of defects found in production. Whatever it is, choose a goal and work on one at a time. Then you judge your success of your process, right? Did you go from 10 hours to 2 hours? No, try something different until you achieve this measurement. Then you start working on the next goal. DevOps changes the objectives. We used to measure mean time to failure, where you try to make sure the server never went down. That is old school thinking. We need to go from mean time to failure to mean time to recovery. You anticipate that the server will go down. Just be sure you can recover quickly. If your applications are built as a collection of microservices, deployed in containers as multiple instances, you can recover quickly by bringing up a new container. And your customer might never even know that the service went down because there was no single point of failure. Containers may be continuously going up and down, but if you can recover quickly by spinning up a new container, who cares it went down? The customer never noticed. It's a whole new way of thinking about availability. In this video, you learned that you should measure and reward what you want to improve. Measuring social metrics leads to improved socialization, and measuring DevOps metrics allows you to see progression towards goals. DevOps changes the objective of problem resolution from failure prevention to failure recovery. After watching this video, you'll be able to identify the limitations of vanity metrics, describe the value of actionable metrics, and list examples of actionable metrics. Beware vanity metrics. Vanity metrics are good for feeling awesome, but bad for taking action. For example, consider the metric of hits to a website. You might proclaim, "This is awesome, we got 10,000 hits to our website." But what does a hit mean? What does a hit represent? Did one person nervously click 10,000 times? Did 10,000 people click once and go away? You don't know. You don't know what action you should take next because you don't know what action drove the visitors to your website in the first place. And so you don't know what action to take next. The number of clicks alone is not an actionable metric. It indicates activity, but you don't know if it's good activity or bad activity. And in most cases, it's not a very helpful metric. Instead, you want to use actionable metrics. Consider this. Imagine you add a new feature to your website and you initially introduce it using A/B split testing, in which 50% of the customers in Group B see the new feature, and then the other 50% in Group A don't. A few days later, you compare the revenue you've earned from each customer group, noticing that Group B has 20% higher revenue per customer. Think of all the decisions you can make. Obviously, you want to roll out that feature to 100% of your customers to start increasing revenue from all of them. You might continue to experiment with more features like this one. Now you have a cause and effect. You know what you did, and you can take action to get more or less the same desired outcome. Realize that you also probably discovered something that's particularly valuable to your customers. This is the power of actionable metrics, so make sure your metrics are actionable. Here are some examples of actionable metrics. These come from Eric Ries, author of The Lean Startup. Reduce time to market for new features. It's very important to be able to get new features out to delight your customers as quickly as possible. Increase overall availability of the product. It doesn't matter what new features you introduce if the product isn't available for your customers to use them. Reduce time it takes to deploy a software release. This is part of the first metric, but focuses on deployment once the release is ready to ship. Increase the percentage of defects detected in testing before production. It's very important to detect defects as early as possible. Another way of looking at this is reduce production level defects. Make more efficient use of hardware infrastructure. This directly affects your cost of goods sold. If you reduce cost, it means more profit. So efficiently using the resources you already have is something you can measure and act on. And providing performance and user feedback to the product manager quickly. Having information when it matters is important for making informed decisions. At our 2017 talk entitled Tools Won't Fix Your Broken DevOps, Nicole Forsgren identified what she considers the top 4 actionable metrics. The first is mean lead time. How long does it take for an idea to get to production? From the time your stakeholder asks for the new feature, how long does it take that feature to get into their hands? The second is release frequency. How quickly can you release things? Hopefully, as quickly as you need and no sooner. You don't want to be disrupted by a competitor and take a long time to respond. The third is change failure rate. When you push things out, how often do they fail? You want to make sure that while you can release quicker, changes aren't failing when they are deployed. Speed is meaningless if it destabilizes the system. The fourth, mean time to recovery. How long does it take when something does fail to recover from the failure? Instead of being concerned with mean time to failure, you want to be resilient to fail and recover quickly when it happens. In this video, you learned that vanity metrics may be appealing at first glance, but offer limited actionable insights. Actionable metrics provide meaningful ways to measure your process and work towards goals. DevOps actionable metrics include mean lead time, release frequency, change failure rate, and mean time to recovery. After watching this video, you'll be able to identify relevant statements for measuring team culture. At first, it may seem that measuring your team's culture would be hard, but it doesn't have to be. I want to share with you a set of statements developed by Dr. Nicole Forsgren when she was the CEO and Chief Scientist at DevOps Research and Assessment, DORA. These are culture statements for measuring the teams on a scale of 7 strongly agree to 1 strongly disagree. On my team, information is actively sought. Do you strongly agree or strongly disagree? By information, we're referring to people being curious about why things happen. On my team, failures are learning opportunities and messengers are not punished. We've all heard the term, don't shoot the messenger. People are not going to be open and honest about reporting what's really going on if they think they will be punished for uncovering something unpopular. This goes even further than that. Instilling in your team the notion that every failure is a learning opportunity is critical for fostering a culture of experimentation where it's okay if experiments fail. It's also getting at the heart of something bigger. No one comes to work wanting to bring down production, but occasionally it happens. It's not the person who failed, but rather the system that failed the person. What could have been done to give that person better information or better training or fix whatever it was in the system that failed them? What this question is really asking is, do you have a blameless culture? It's very difficult to foster a blameless culture, which is why it's critical to ask questions about it. On my team, responsibilities are shared. This is measuring the feeling that we're all in this together, right? There's no such thing as a hole on your side of the boat. When things blow up, everyone pitches in to solve the problem or clean up the mess. On my team, cross-functional collaboration is encouraged and rewarded. This goes back to the measurement system. Are people being measured on being collaborators, or are people being rewarded for being lone contributors? Remember, you get what you measure. This question measures whether people feel they are being rewarded and thus encouraged to collaborate. On my team, failure causes inquiry. Again, this is not a whodunit inquiry, but rather a where did the system fail the people inquiry. What was the root cause, and how can we prevent it from happening again? This is also about continuous improvement. How can we learn from failures and get better? On my team, new ideas are welcome. This is critical for ideas to flow openly. Do people feel that their input and ideas are listened to, or are they getting shut down or paid lip service? You can tell a lot about the health of your team dynamics by understanding if everyone feels welcome and contribute their ideas. You may feel that it's difficult to measure your team's culture, but really, I like Nicole's approach and wanted to share it with you. In this video, you learned you can rate statements developed by Dr. Nicole Forsgren to measure your team's culture, including statements about information, failures, collaboration, and new ideas. After watching this video, you'll be able to recognize how site reliability engineering differs from DevOps, recognize the commonality between site reliability engineering and DevOps, and explain how site reliability engineering and DevOps can be used together. You might be wondering how DevOps compares with site reliability engineering. Before we can explore this topic, we should probably describe what SRE is, how it differs from DevOps, and how you can leverage SRE in a DevOps environment. According to Benjamin Traynor Sloss, SRE is what happens when a software engineer is tasked with what used to be called operations. Most systems administrators are happy doing the same manual tasks day after day, perhaps because they feel it's their job to do these manual tasks. But if you ask a software engineer to build a server, now they'll probably do it manually the first time. A few days later, you ask them to build another server just like a first one. They might do that one manually as well. But by the time you ask for the third server, a software engineer is going to start writing a program that builds the server for them automatically. That's just how software engineers think. They're programmers. They write programs. The goal of site reliability engineers is to automate themselves out of a job. Of course, that will never happen because there's always more things to automate. One of the tenets of SRE is only hire software engineers, right? You want people who know how to write code so they could automate repetitive tasks using infrastructure as code. Site reliability engineers focus on reducing toil, that is repetitive manual tasks. It's recommended they spend about 50% of their time reducing toil through automation. The idea is that anything you do repeatedly should be automated. You shouldn't be doing the same manual task day after day. SRE teams are separate from development teams. This is a big difference between DevOps and SRE. DevOps is the recognition that working in separate silo teams is inefficient. But SRE, on the other hand, keeps those silos in place. The development team is a separate and distinct team from the operations team. In SRE, stability is controlled through something known as error budgets. Developers are allowed to deploy their applications to production as long as they don't cause too many production outages. The upper limit of allowed outages caused by errors is the error budget. So let's say you've got a service level agreement of 99.9% uptime. That equates to about 44 seconds per month of downtime. As long as the outages are below 44 seconds per month, the developers are free to keep deploying their releases to production. Once developers have caused enough outages to exceed the error budget, they're no longer allowed to deploy to production. This actually works pretty well. It solves the problem of developers waiting for operations, yet it still gives operations control over the stability of the production environment. One last thing about SRE is that developers spend about 5% of their time rotating through the operations team so they understand what the SRE team is doing on a daily basis. Also, if they cause too many outages or the toil exceeds 50% of the site reliability engineer's time, more developers are shifted to operations to help bring things back into balance. There's a big difference in teaming between SRE and DevOps. As we've learned, SRE maintains separate development and operations teams, but it does have one staffing pool. That means you need another site reliability engineer, you take away one of the developers. You want another developer, you take away one of the site reliability engineers. This is an effort to balance things out. DevOps, on the other hand, breaks down the silos, right, into one team, one common business objective to deploy software to production quickly and safely. The other big difference between DevOps and SRE is how they maintain production stability. As we said, SRE uses error budgets for development it has to comply to, and those are based on service level objectives. When a developer exceeds the error budget, making production unstable, they can no longer deploy to production. In contrast, DevOps maintains stability by using automation through continuous delivery pipelines and by making sure that everyone is responsible for the code that runs in production. DevOps has this you build it, you run it mantra. Unlike SRE, developers are responsible for their applications in production. There's commonality between the two practices. Both seek to make development operations visible to each other. Right? Whether you have developers rotating through operations as in SRE, or you have development operations on the same team as in DevOps, everyone understands what it takes to keep production stable. Both require a blameless culture. No one comes to work wanting to take down production. It's usually the system that fails the people, not the other way around. So having a blameless culture is important in both practices. People can speak openly and honestly about how things are going and how to improve things. The objective of both is the same, to deploy software faster with stability. So DevOps and SRE do have common goals. They just achieve them in completely different ways. When we look at how DevOps and SRE can complement each other and used together, I like to think of SRE as the team that maintains the infrastructure and DevOps is the team that uses the infrastructure to maintain their applications. If you're in a cloud environment, SRE includes the people who operate the cloud. DevOps includes the people who are consuming the cloud. This is why using things like platform as a service is so important to DevOps. The SRE teams provide a platform, the DevOps teams utilize the platform to deploy their applications. In this video, you learn that SRE takes a different approach than DevOps. SRE and DevOps have some common goals. SRE and DevOps can be used together to both maintain and use computer infrastructure.